Yeah, go ahead.
I'm a PhD candidate and the supervision Professor Yan Fu in the School of Data Science at Fudan University. And my research interest is statistical sparsity for learning problem and generative coding.
Okay. And finally, we have Yu Xiang. I'm not sure if I'm saying your name right. You can correct me later from UIUC, who's a professor in Department of Computer Science there. So yeah, maybe with that little bit of introduction to the speakers, we can switch next to the introductory session by Da.
Hi. Do you see my screen?
Yeah, we can.
Is it moving?
Yes, yes.
Okay. Okay, so hello everyone. Thanks for coming to our future learning tutorial. In this section, I will give a brief introduction about future learning, and hopefully after that, you will understand some basics and the current status of future learning research. Yeah, the background of future learning. So first, can we play a game? So there are like 6 images on the left, 3 for echidna, and 3 for porcupine. And based on the example I give you, can you guess the category of the image on the right? Oh, maybe like you can raise your hand if you think it is an echidna.
I put echidna.
And also now you can like raise your hand if you think it is a porcupine.
No.
I actually can't see anything from the side. Maybe Tim, can you tell me the answer? Most people like voted.
Most people voted echidna.
Okay, great. I think yeah. So this is these 2 animals are uncommon to most of us, but I believe from the answer I got, we got the right answer. It is an echidna. So actually, this is something like about like visual future learning. This is human is very good at. Actually, this like visual future learning is some kind of a special gift, because if we can think about something for the other modalities, like for example, if we learn to drive a car or ride a bike, it's actually not that easy to learn that fast. For myself, actually, I got my like 4 driving license in the UK recently, but actually I can't manage to learn the pass the test like driving test, just learning like 1 or 2 like times of like driving instruction. So it's nice that we, as our human, we have this gift. So we also want to enable the computer system to have this ability as well. But we know that like CNN, ResNet, and the recent VIT models, they are exceptional at different vision tasks, such as image recognition, semantic segmentation, object detection, and so on and so forth. But to enable such kind of like exceptional performance for those like deeper models, they typically require training data with similar size as like ImageNet. But however, we know that data annotation is time consuming and expensive. So how can we like use very limited amount of training data to get a decent performing model? But this is hard. Why? Because, for example, this is generalization error bound. Specifically, it's a VC dimension bound. So these bounds tell us that within probability at least 1 minus delta, this bound holds, namely, the true generalization error is smaller or equal to the right-hand side. So we hope the right-hand side is small, indicating that the model is likely to perform well on new unseen data. But if we look at the the right-hand side, the numerator, we can see that there is a VC dimension there. So this VC dimension is the measure of the complexity of the hypothesis class. So normally for the deep models, this VC dimension is very high. So if we want to have a small right-hand side value, so it basically means we need to have a large value of M. M is the size of the training data. So if we want this model to generalize well, so it's very hard actually to learn with a small m. So basically that's why future learning is not easy to achieve. But okay, this is a goal for us. So and okay, I also want to have some distinction between future learning and relevant topics. For example, domain adaptation. So the difference between domain adaptation and future learning is future learning cares about the generalization for a new task. However, like domain adaptation, they care about like the adaptation across different data distributions within the same task. And also like non-tailed recognition. People typically like solve this problem to by training a model on some imbalanced data of different classes. And future learning also have this like imbalanced data problem if we consider the data amount for the base and the novel classes. But this like imbalanced data for future learning actually comes in a sequential way rather than like in the training in the same time. And also like zero-shot learning. For zero-shot learning, it also enables a pre-trained model to recognize a novel class, but actually it doesn't require any training image of that novel class. Sometimes they often have some mapping between the image attributes to some class label space. So when a novel image comes, they can get the attributes and then map to the class label for that image. And also like open set recognition. So for full short learning, we care about the recognition of new tasks or new classes at test time. But for open set, it's actually often try to distinguish between known and unknown samples. And if it is unknown, so basically it will be like neglected. Okay, so let's talk about some benchmarks for future learning. There are many different future learning benchmarks, but here I will briefly introduce some such that you can have a sense of future evaluation. The first one is like Omnica Note. So they're having images for different characters. So basically they are like 1,600 characters from 50 alphabets. And each character has like 20 images with size 28 by 28. And people normally like use 1,200 characters for training and the rest for testing. So this is actually quite a small scale data set. So it's good for us to play with in the very beginning. And also people try to repurpose CIFA 100 for future learning. They split the classes for different splits for training, validation, and task. And each class have like 600 images. And also some researchers created a subversion of ImageNet for future learning. So they randomly selected 100 classes from ImageNet, and each class contains like 600 images with a downsized image resolution. And then they use like 64 for training, 16 for validation, and 20 for testing. And also like later on for this benchmark, people started using like larger resolution images because they found this can boost the performance. Okay, here I will give a little bit more like description how people normally do this like future evaluation. So like I said, people normally treat 1,200 characters as the base classes. So we can think about this is the the meta trend dataset. And they use the 420 classes for testing. Those are like novel classes. So basically what they do is normally they just use the base classes to train a base model in whatever way you are interested. And then they will do some episode sampling at the test stage. For example, here, so they normally like sample it in like K-way and N-short. K-way means like K different classes, and N-short means like N support images for each class. So in this example, it's a 20-way and 1-shot. And more precisely, what is conducted is we use a meta trend dataset to train a like feature extractor, and then we can use the support set image to generate a classifier for this specific episode. For example, for this query image, we can go through this feature extractor and the classifier. Then we want to get the label 2 among these 20 like classes. Yeah, and also we will get the accuracy for each episode, then average the accuracy across many different episodes to remove the randomness of different like sampling. But one thing people realized is because it's common people use like the fixed K-way and N-short for their data sampling or episode sampling. Actually, when the model is evaluated at a different way or shot, the performance will degrade. So actually, it means the meta learner or the future learner, it got overfitting to this way and short protocol as well, which is something we don't want to have. And also, this is probably the most challenging benchmark at the moment. It's called meta dataset. It's released by some Google researchers. So you can see that this dataset contains 10 different datasets. So like they have ImageNet, OmicNode, which we introduced before. And also they have like fine-grained image recognition as well, like the aircraft or birds. So here the categories are different types of aircrafts or like different species of birds. And also they have like a image depiction like sketch and other like stuff. So basically you can see that this is quite a challenging benchmark. This is some like class numbers for different different data sets. So you can see there are massive amount of classes. By talking about this meta data set, actually I also want to introduce a little bit like different settings in feature learning. So in the example I presented in the OmicNode meta train and meta test protocol, even the classes in the test stage is different from the training stage, but they are still from the same dataset, OmicNode. But sometimes people, but actually, this like within same dataset evaluation is not always guaranteed. So people started doing like a cross-domain feature learning, so they can meta train on a dataset like ImageNet. Then they got evaluation on the other dataset. So they call it like cross-domain feature learning. But of course, you can understand this is more challenging because the domain shift between the meta train and the meta tested data are like larger. And also they have the generalized feature learning. So because traditionally people only care about the performance of evaluating on those novel classes at meta test stage. But the generalized feature learning also cares about the performance of the base class. So they care about the base and the novel classes in the same time. And also like few short class incremental learning. So basically, in this situation, those novel classes are coming actually in a sequential way, like one by one or a few by a few. And in this way, people try to have a good performance on the novel class, but also they try to retain the performance for the classes like came in the the performance for some older performance for some older classes. So they don't want the model forget the performance of some older classes. Yeah. Yeah, those are some like benchmarks or setting I want you to go through. But for more like details or the leaderboard performance, you can go to the papers of code. You can find some like state-of-art. You can find more like state-of-art performance in this page. And so far, I have only talked about like future learning for image recognition, but actually, it's not only about recognition or classification. People also worked on like regression problems. So basically, how to train a model on some known 3D objects with a corresponding rotation angles. Then the training model can infer the normal rotation angle of a novel 3D object with knowing just a few rotations. Yeah, this is kind of sound like a regression problem. Also, like people care about dense predictions as well, like segmentation. So basically, how can we generalize a model to a novel class with just only a few like support images with the mask annotations? That's also something we care about. And also, like there are some research, there are some works about like a future learning for object detection. So now the support image is with some like bounding box annotations, and if we want to have good performance on this like a future learning for object detection. And then nowadays, NERF is quite popular, which conducts like a 2D to 3D like reconstruction. But actually, this is also a future learning problem because people want to use very limited 2D views to have this precise 3D reconstruction. And also like a reinforcement learning. So this is a maze map. So for example, if you learn like an agent on some simple maze, and how can it adapt to some like novel maze maps with just having a few trial and error experience. And I think for this, for those like applications, I think Yusheng will talk a bit more in his talk. Okay, so far when I talk about those benchmarks or applications, it's only about the evaluation like within the same task. For example, the image recognition, we train on some base classes and then we test on some novel classes, but that's still about image recognition. So how about we evaluate the performance of future learner across different types of tasks? So in this CVPR, we got a one paper accepted called Meta Omnium. So this benchmark is to evaluate the future learner or meta learner that even if you meta train on a segmentation, but then you can get evaluated or generalized to some other even like medical diagnosing problems. Okay, yeah. Feel free to get access to this like link if you are interested. Okay, now I would want to briefly talk about some conventional future learning methods. The mainstream of like future learning methods are kind of like meta learning methods. So meta learning methods, I mean, different from the conventional methods, meta learning methods treat the entire optimization pipeline as trainable modules, including the model initialization, learning rate, and even optimizer, and so on and so forth. So, for example, some researchers, they, instead of using an SGD optimizer or other conventional optimizer, they define the future learning optimizer as a learnable recurrent neural network, which inputs the model parameters and support data, and outputs the final updated model parameters. And for training this kind of like meta learner, they often conduct some kind of episodic training, episodic sampling from the training data set to form some virtual future learning scenarios. So basically, for example, this is a 5-way one-shot. So they will feed this support set together with the parameters, and then they get this evaluation or the evaluation of the updated model on this virtual query set. Then they will minimize the loss. Then they can optimize the loss to get the meta learner for this optimizer. And similarly, they can use a similar episodic training to optimize the model initialization. Then the model can adapt fast for the downstream novel task. And also people try to meta metric function to measure the distance between the query and the support in feature embeddings. And okay, there are also some others. I probably will not introduce them here. Meta learning methods, they're often exceptional, but they require some kind of special training strategies. For example, like episodic sampling, and sometimes it can require more computation cost because of the high order gradients during the meta optimization. Actually, people found that sometimes the simple method like fine-tuning works pretty well. For example, this is the work in ECVP 2020. They found that simple fine-tuning at the meta test stage can outperform almost all the previous meta learning methods. Of course, this in this cross-domain future learning evaluation, the meta test domains, they are quite diverse to the source domain. So maybe in that scenario, meta learning prior it's not sufficient for the downstream, the performance of the downstream classes. And also some people just propose to use a very simple nearest neighbor method. So they extract the feature for the support and query data, and then they form this nearest neighbor classification. But they found that the key factor for this nearest neighbor classifier is they need to do kind of some centering and a normalization of the feature such that it can have a very good generalization performance. So you can see that it's by having the centering and the normalization CO2N, the final performance is quite decent. And also some researchers really try to improve future learning by statistical tools. For example, this is one work by another speaker. They try to use improve future learning through some unlabeled data. So they use some lasso-based linear regression model to help select the most reliable pseudo labels for the unlabeled data. So then they can use those pseudo label to help train the future learner. Okay, I think he will talk a bit more about that later. And also some use the causality. So some work assumes a distribution shift between training and the test, sometimes caused by the selection bias, which can induce spurious correlation between the causal feature and non-causal features. So they propose such kind of argumentation, like patch mix that exchange patches from different images to form new training images. And in this way, they found it helps the model to discover the causal features for future learning. Okay, so what about the status of future learning lately? So we know that foundation models are playing important roles in our daily research. They're very powerful, they lend very good knowledge from large-scale data set, basically a good prior. This is work actually done by our team in last CVPR. So we actually found that instead of focusing on designing complicated meta learning methods here, we actually found that the foundational pre-training and the test time fine-tuning has a big influence on the final performance. So basically, you can see here, regardless of meta learning or not, you can see different pre-training strategies makes the performance quite different. And also like this is the test time fine tuning. So you can see that if you really fine tune the model like sufficiently or adequately, the performance can be very different. And by having this like foundational pre-training and the test time fine tuning, we actually reach the state-of-the-art performance in this challenging metadata set. And also more recently, some researchers found based on the good foundational pre-training, we can just do some parameter efficient fine-tuning at test stage. So then it can achieve some state-of-the-art performance. So in this way, actually, we don't really need meta training. So we just need the very basic foundation model pre-training, and then you just deploy the pre-trained model to the final test classes. So it can achieve very good performance. I think another speaker, Yan, we will talk a bit more about this. And also like visual in context learning. So we know that in natural language processing nowadays, prompting has recently emerged as a way to facilitate a training model for a new task without any further training. They call it in context learning. And some researchers also started exploring in context learning for visual tasks. So basically the goal is that after giving some visual demonstration of a specific task, the model can conduct the same task on novel query images. So the way they do it is they treat this as image impending problem. So basically these are kind of like a demonstration of the task, and this is a query image. Then after feeding this to the impenter model, you can get the answer or get the prediction for this query image based on this task description. And in this example, it's basically a one-shot problem. So basically you have a one-shot support set to define the task, and then you can do this task for any query images. But of course, it extends to future scenarios straightforwardly. And also like people started working on like multimodal in context learning. So the trained model can learn with a few support VQA examples. Then they can predict the answer for a novel question based on a novel input image. So basically here you can see an example. Given this support image, it says this person is like a smile emoji. And this, the second, it says the person is like a sad emoji. And then the model can predict the image for this new input image. Okay, so I think that's the overall status and basics for future learning. Actually, so this is the take home I want to give. Actually, when I was trying to think about the take home message, I found that one paper got accepted in this CVPR. It's called prompt generate and catch. So cascade of foundation models for making makes a strong future learners. So I think this is probably something I was also trying to pitch in the end, because we know that foundation models are okay, more concept is for this paper, they try to take advantage of different foundation models to build a very powerful future learner. So they use the language generative knowledge from GPT-3, and they use the language vision contrast knowledge from CLIP, and vision only contrastive knowledge from Dino feature. And also they take advantage of the vision generative knowledge from DALI model. So I think this is something trendy because foundation models are more and more powerful. So how can we use the specialty of different foundation models to build a strong and generalizable model? That's something we really should consider. And I think this is a good example for that. And okay. Yeah, I think this is the introduction section from me. Hopefully you now can have a sense of this, the basics of few-shot learning, and have a brief understanding of the status of few-shot learning now. Okay, thanks.
Mute probably. And
With
switch on video.
the mute option.
Video, yeah. Okay, and then share on screen probably this. And then okay. Does it look okay? Can you see online? Oh, why you can see it?
Not yet, not yet.
Started screen sharing. Do people online see my screen?
No, it's show that CVPR tutorial has started the screen.
Oh, resume. Why it's paused? Is currently the host. Oh, allow recording. What? Try again. Hybrid meetings are so confusing. Why it doesn't resume?
Okay,
Oh,
okay.
no, okay. Okay, cool. Hopefully all the IT is working. Great. So yeah, I'm Tim Hospitalis from University of Edinburgh and Samsung AI. And in the second session, I'll talk about meta learning approaches to few-shot learning. So as Da already introduced, we have a lot of reasons to want to do few-shot learning, whether that's rare categories, expensive to annotate data, or one of the most interesting ones is emerging categories. Maybe there's new products coming out in consumer electronics companies or new brands coming out, and these are always new categories emerging, which we might want to recognize, and then there's, by definition, not a lot of data for them. And as Da said, this is kind of hard because most of the time, if you've got a lot of data for every category, you can do super well, as we know from ImageNet, etc. But then if you go all the way down to one example per category, the performance drops off dramatically. So yeah, it's a tough problem. And this is, of course, because of the overfitting problem. As you know, when you have the large data regime, everything works well. When you have in the small data regime over here, typically test error is much worse than your training error. So it's a big problem to solve. So all of the solutions out there to few-shot learning that I know of involve borrowing some kind of related data from elsewhere. So there's approaches based on part-based learning, for example, going back to the famous Science paper in 2015, where they are recognizing new letters or object categories based on parts that they already learned from old object categories. So you're kind of borrowing knowledge at the part level. There's transfer learning approaches like what Dad just talked about, where you focus on learning a deep representation from large data sets and transferring it to help you solve a new data set of interest. And then there's meta learning approaches, which are all about how to optimize your learning algorithm on some auxiliary tasks so that it becomes more data efficient for target tasks. And these meta learning approaches are what we are going to focus on in this session. So in the first part, I'll talk a bit about some kind of overall concepts for meta learning, which will be helpful as a kind of mental framework to understand all of the tools that are out there. So one way to think about meta learning is that we are trying to learn something about the learning algorithm. So in past shallow learning days, you might learn your classifier or your regressor, but you hand designed your feature extractor with SIFT or whatnot, and then you did SVM or something for the learning algorithm. And then in deep learning days, okay, you learn the feature extractor as well, but your learning algorithm, whether that's your architecture or your optimizer or something that's hand designed, and meta learning is all about whether we can also learn something about the algorithm as well and try to find what kind of algorithm will be more data efficient. So to be slightly more formal about that, it's helpful to go back to the definition of machine learning in the first place that Tom Mitchell gave in '93. So he said, if you have got a task, some experience drawn from that task and a performance measure, then we say that a program is doing machine learning if its performance improves as a function of the amount of experience. So of course, some kind of handcrafted algorithm will do the same thing every time. Flat performance with experience and ML algorithm will get better. And so then building on this kind of idea, Sebastian Thrun in 1998, talking about learning to learn, which is more or less a synonym to meta learning. He said, if we've got a distribution over tasks and our learner's performance is improving as a function of the number of tasks that it's seen, then we call it learning to learn. So a conventional machine learning algorithm that is learning from scratch every time will have a performance that doesn't change as a function of the number of tasks, but a meta learner or something that's learning to learn well. So we can imagine schematically, if you've got a couple of different things like standing, running, kicking, you are trying to learn. What we want to do is to learn something from those auxiliary tasks that will help us to learn more efficiently in a target task, dancing or whatever. And we call this inductive bias sometimes in machine learning theory. What kind of inductive bias will help us to succeed with smaller training sets? And there's a lot of different kinds of inductive bias we can extract from our auxiliary tasks, whether that's priors in a Bayesian sense, representations, etc. And we'll go through some of these later. But first, here's a small example of human meta learning that I can hopefully convince you of the general idea. So suppose I asked you to draw a regression line through these three data points in the top right over here. What kind of line would you put through them? You might be thinking this is slightly ambiguous because there's only three data points. It's hard for me to put a high confidence line through those three. So what if I told you there's a whole distribution over tasks, and these first n tasks were the first n tasks in the distribution? Does that help you to be any more confident about how you would draw this line? Any thoughts? Or alternatively, what if I told you that these were the first n tasks over here before this final testing task over here? Do you have any new idea how you would like to draw the line through the testing task over here? So hopefully you can see what I'm getting at here, that in this first task distribution, you might be thinking, okay, it looks kind of linear over here, so I'm going to draw this line through the testing task. And in the second set of tasks over here, you might be thinking, okay, it looks kind of quadratic over here, so I'm going to draw another line through the testing tasks. And in this particular case, so here the inductive bias that you might have transferred when thinking about this toy problem is basically the choice of regression kernel. And so that's kind of one example of something which you can transfer if you know that tasks come in some kind of task family. Okay, so getting a little bit more concrete, when we do supervised learning from scratch in a kind of MAP sense, we might be trying to solve something like this optimization here. And if you are familiar with graphical model plate notation, you've got some kind of input data X, some labels Y, and this plate around them means there's a whole bunch of them. And this other theta outside of the plate is a model parameter, which is telling you how to predict the labels from the inputs, right? But now let's suppose there's a whole bunch of other related tasks in this italic, the auxiliary tasks or meta-train tasks, we call them sometimes. And now the question is, how can we figure out how to fit our model theta given both the target task of interest and the related tasks? And so to do that, what we do in a Bayesian sense is to add a kind of another layer of model hierarchy. So we've got some kind of hyperparameter omega, which is telling us something about how to learn, the specific model theta, which is going to be for each of the tasks. So these were like all the thetas we saw here in the toy problem. And this omega might be something like our regression kernel, right? And in a Bayesian learning sense, you want to say, okay, what's the distribution of a how to learn, for example, regression kernel given these auxiliary tasks, and then use that to solve the target task of interest. And if you are Bayesian, okay, you don't know this omega either, so you integrate it out. That's typical Bayesian thing to do. If you're not a Bayesian, you might say, let's find the most likely how to learn, e.g. regression kernel from the auxiliary tasks, and then use that to solve the target task of interest. And so this operation of finding the most likely how to learn given your auxiliary tasks is the kind of key meta-learning operation that we are going to be interested in. So as we said, there's two steps. The first step is to find out this how to learn, like the regression kernel, and then we can deploy that for solving a new task. So for finding out this how to learn, typically what we are going to do is we are going to say, let's get a whole bunch of training tasks, put them through some kind of learning algorithm, and then get out the model, evaluate it, and then search for the best learning algorithm. So one thing important is that we want to split our data for each task into training data and validation data. And we want to do the learning on the training data and then evaluate the learning algorithm on the validation data. So in graphical model notation, that means we've elaborated the graphical model slightly like this. So for every task inside here, we have got a train set where we observe because it's gray here, the data X and the labels Y, and the val set where we observe the data and not the labels for the real test tasks. And so we basically want to do inference in this graphical model. And this is the first kind of important point. If you compare this kind of meta-learning, or two kind of variants of the meta-learning setup that you might want to try and do, you might say, let's put our training set into a learning algorithm and get out a model parameter, then evaluate that model parameter also on the train set, or put our training set into a learning algorithm, get out a model parameter and evaluate that on the val set. The difference between these is, of course, one of your favorite deep learning memes, right? So if you do the top one of these, you would be meta optimizing for overfitting. If you do the bottom one of those, you would be meta optimizing for generalization. So actually, sometimes in meta learning, people do the top one of this. That's normally if you're doing meta learning of an optimizer. So you just say, I want my optimizer to converge as well as possible. I don't care if the point that it converges at is generalizing well to the training or testing set. But for the purpose of few-shot learning, we are normally interested in this latter one of meta optimizing for generalization. And the other important point to make about this is that when we solve this meta optimization, we will normally put small training sets in here. So if when we solve all of these auxiliary tasks, we put in the small training sets and we check their generalization performance, we are then kind of meta optimizing for generalization after few-shot learning. So to summarize where we arrived at, the overall framework that we're going to have often comes out as this kind of bi-level optimization. So in your inner loop, you solve a particular learning problem on a training set using a particular algorithm, omega. And if you look at something like this, this looks like your normal kind of solving a neural network learning. We can also wrap up that solving a neural network learning problem inside a function, so we can encapsulate this training algorithm. Sometimes you write A here to summarize the algorithm, and this algorithm might be doing gradient descent, or it might be doing whatever else, but either way you get out the model parameter. And then we are going to put that model parameter in here, so from here to here, right? And then evaluate performance on the validation set. And then we sum that over many splits of training and validation sets. and then we optimize that final validation performance with respect to our how to learn. And so typically in the inner loop here, we might train a neural network. In the outer loop, we then might take derivatives with whatever aspect of the training algorithm we are trying to meta optimize. And so there's kind of three important things to note about this outer loop. So one is what we are optimizing for. As we mentioned earlier, if you put the kind of small train sets in the inner loop and the validation set in the outer loop, you're optimizing for few-shot generalization. You can put other things here, but for the purpose of the current talk, that's always what we are going to be doing. And the other is what we are going to meta optimize. So what this placeholder omega is can be all kind of different things. It can be Bayesian priors, it can be neural architectures, it can be optimizers, can be hyperparameters. We basically want to tune all of those things to make sure to improve the data efficiency of this inner loop algorithm. And then the third important point about this is how to meta learn. So so far there is this kind of abstract notion of minimizing this loss with respect to the learning algorithm. So we could take derivatives with respect to omega if it's something continuous and everything is differentiable, or if something is not differentiable, we might do evolutionary optimization for omega. So there's different things you can plug in here. And so this kind of inner outer loop bi-level optimization runs over all of our auxiliary tasks. And then once we've solved how to learn omega star, we deploy that to our new kind of testing task, for which we plug in the training set, learn the new solution, and then we finally do inference on that testing task. So this is the kind of little bit whirlwind tour, but just to give the high level summary of how all of these things work. Everybody cool so far? Any questions? No? Okay, great. So so that's the very high level view. And so then within that paradigm, there's two kind of popular families of meta learners. So one are gradient-based meta learners and the other are amortized meta learners. So I'll talk a bit about those in turn next. And by the way, if you want to know more about meta learning, you can check the survey that we wrote a couple of years ago in PAMI. So as you saw when I wrote this bi-level optimization, this inner loop problem, when you actually train the neural network, something like this looks like what you are normally doing, where you might solve this with gradient descent. And then this weird thing here where we kind of feed our training set into a function and get out a model. So these two things, you can kind of, if you abstract away the whole gradient descent algorithm and pack it into this function here, A. So that's why I put this kind of equal between them, right? But basically there are some algorithms which are more natural to look at like this and others which are more natural to look at like this, right? So first we are going to look at the gradient descent algorithms that are more natural to look at like this. So I'll just mention first the most kind of famous one in this space, which is MAML. Probably most of you already know about this. So the context of MAML is that in non-convex optimization, such as the schematic here, you are kind of going downhill on your training loss, and the final minima that you get to depends on your starting point. So if you start here, you arrive to here. If you start here, you arrive to here, etc. And so the especially in the few-shot learning regime, whatever minima you find is likely to be poor. And so what MAML says is, can we reason about what's a good starting point and find a good starting point, which when we go downhill from that starting point, we arrive to a minima that generalizes well, right? So this is what MAML said all the way 5 years ago now. Time is flying in ICML 17, 6 years even. Yeah. So expressing MAML in terms of this kind of generalized framework that I gave before, in the inner loop, when you solve your model optimization, they basically just express that as this. So we start from a starting point omega, and then we do one gradient descent step on the training data set with respect to omega. So sometimes they do one or maybe 2 or 3, basically a small number of gradient descent steps. But then when you solve this whole meta training optimization, you are searching for the initial condition omega, from which when you do one or few gradient descent steps, you end up with high validation performance. Right? Everyone remembering MAML? Yeah, so the very big assumption here is that you can solve the whole deep neural network learning problem with 1 or 2 gradient descent steps if you are allowed to carefully choose the initialization, right? And then, so in the meta training step, we are going to search for a good initialization over a whole range of meta training problems. And then in the deployment step, we start from that carefully chosen initialization W star, and then we do 1 or 2 gradient descent steps on our new problem and hopefully arrive at a good solution. And one thing I didn't say explicitly here is in the outer loop step, most of the time in mammal, you just also take derivatives with respect to omega and you do gradient descent on the initial condition in the outer loop of having done gradient descent in the inner loop. And the good thing about this is because everything is done with gradient, you can scale to high dimensions. So the hyperparameter you are searching here in mammal is the same number of dimensions as the actual neural network that you are trying to train. And so sometimes people ask, like, what's the connection between meta learning and HPO? And they kind of, the answer to that is that they arose in different communities, but eventually they kind of become the same thing. But one of the differences is that in meta learning, because you are normally doing gradients in the outer loop step, you can have very high dimensional hyperparameters like the initial condition of a neural network, whereas HPO people don't as often do gradients in the outer loop, so they are searching at the hyperparameters that have lower dimensions than millions. Okay, so that's the kind of starting very classic meta learner. So what's been happening in the field since then? I'll discuss a bit about 3 kind of major trends that have been happening since mammal. So one is about efficiency. So because you have gradients in your inner loop and gradients in your outer loop, you usually need to do high order gradients to solve things like mammal. And you also might need to store the whole compute graph if you're doing reverse mode differentiation. So you need an amount of memory that's proportional to the number of inner loop steps. So this is something which is kind of annoying in few-shot learning, but not quite fatal, because there might only be 1 to 5 or something inner loop steps, not thousands and millions of inner loop steps, but it's still a lot of memory, which makes it hard to scale mammal to like big neural networks, for example. So then there's a whole bunch of things people have been doing: first order approximations to alleviate the high order gradients, doing forward mode differentiation rather than reverse mode differentiation to reduce the memory consumption, doing implicit gradient to reduce the memory consumption, replacing the outer loop optimizer from gradient descent to evolution, which is also for then removes the second order gradients if you do evolution in the outer loop, because you no longer have derivatives of derivatives, or even things like distillation to remove the high order gradients. So basically a lot of different things people have been doing to try and make this stuff faster and reduce the memory consumption. So I'm not going to talk in detail about these things, but if you're interested, you can follow up those references. Another big trend of things that people were doing in meta learning is to think about what aspect of the inner loop you can optimize to make it faster, more data efficient. So all of these equations are just snippets of the inner loop assumption of many different papers. So in mammal, they say, let's start from this carefully chosen omega and do 1 gradient descent step. In meta HGD, they start from a carefully chosen initialization, but then also have learned a learning rate for each of the parameters. So now you're learning like double the number of parameters in your neural network, both in initialization and the per parameter learning rate. In various editions of sparse mammal, they try to have something like this. So they are trying to learn like which parameters of the neural network you freeze and which parameters you update. In meta curvature, meta MD, they are trying to learn a whole preconditioning matrix. So you don't just learn a learning rate for each parameter, but you learn the whole curvature of your optimization problem, etc. And then there's a whole bunch of neural optimizers that, rather than having a kind of conventional gradient descent that looks like these, they basically feed the gradients into a neural network and let the neural network train the next step. So basically all of this are slightly different assumptions of what your inner loop optimization looks like. And in each case, you are kind of tuning the blue-green-ish meta parameter here to optimize your outer loop validation performance. So that's like one of the big trends, trying around with different parts of the inner loop optimizer. And just to recap, so the reason mammal is avoiding the overfitting is one, because you carefully chose this initial condition, but then also because you only did a few inner loop steps, right? So you can't overfit that much if you only do 1, 2, 3 inner loop steps rather than hundreds of thousands of inner loop steps. But one problem is that this number of inner loop steps K is something which is kind of hard to optimize in the original mammal formulation. So one of the things people tried to do to alleviate that, for example, in implicit mammal in Europe a few years ago, is to say, let's do the gradient descent steps, but also regularize our neural network parameter theta to stay close to the carefully chosen initial condition. And then hopefully that also reduces the amount of overfitting that might happen, even if you slightly overestimate the number of inner loop steps. But you still have the problem that you can't efficiently meta learn this lambda, which is basically how much you are trying to reduce overfitting in this update, right? So one of the things that we worked on, a variant called camel, basically says, let's do the gradient descent steps, but if we start to drift more than a distance rho from the initial condition, so we are learning theta, this was our initial condition. If we drift more than a certain distance rho, then we project it onto the sphere of radius rho. So we basically cap the distance that we are allowed to move in weight space. So in this typical like mammal schematic, we are learning a sphere of radius rho around which all of these different task-specific updates can't get more than rho radius away from the starting point. And there's two reasons why we want to do this, one of which I'll come to later. But the first is that it removes the annoying hyperparameter of how many inner loop steps to take. So now this x-axis is your number of gradient descent steps in the inner loop. If you do regular iMammal, you quickly start to overfit after it becomes too many. But if you now have this maximum radius that you are allowed to travel, then you can remove the hyperparameter just by setting k to a large number, and you don't overfit in your inner loop. So that's some stuff in this kind of trend of like changing how the inner loop optimizer works. There's like so many hundreds and thousands of papers in that space. Could talk all day, but actually I think a more interesting trend, rather than playing around with hyperparameters of conventional optimizers, is looking at different kinds of meta parameters to learn in the first place. So for example, one thing people do sometimes is to have some kind of stochastic neural network dropout or something like that, and you can try to meta learn the dropout parameters to improve your generalization. Even more interestingly, there's work which says, let's treat the neural architecture as a hyperparameter to learn. So normally you might just take a ResNet or a VIT or whatever to try and do your few-shot meta learning, but this might be kind of overkill for a few-shot learning problem. So you can also say in your outer loop, let me treat both the initial condition and the neural architecture, and then let's search for a neural architecture which leads to good few-shot learning in the inner loop. So there's been a couple of papers trying to do that. So I think this space of like, you're looking for new problems, this space of like looking for more innovative aspects of the learning problem to do meta learning on is maybe more interesting than all of this tweaking around with optimize inner loop optimizer. So anyway, just to finish this section, I can mention two kind of state-of-the-art few-shot gradient-based meta learners. So one is Unicorn Mammal that came out last iClear, and basically this is looking exactly at the very classic mammal algorithm, but kind of tweaking. And well, for context, if you don't follow this space a lot, many other recent papers surpassed classic mammal a lot in few-shot learning benchmark performance. So people were beginning to ask whether it was still relevant. But Unicorn Mammal, they basically like tweaked a few things about mammal and then caught all the way up to the benchmarks again. And one of the main things they tweaked is to change how you deal with the feature extractor and the final classifier layer in mammal. So in this final classifier layer, one problem is that in those few-shot learning episodes that Da was talking about earlier, like normally the classes are shuffled every time. So first you might be recognizing dog versus cat, second might be cat versus motorbike. And because the classes are shuffled, it pretty much doesn't make sense to learn an initial matrix for this output layer. And so if you change it to learning an initial vector for the output layer instead of an initial matrix so that it becomes permutation invariant, then all of a sudden you catch up on the leaderboards again. So anyway, that's a Unicorn Mammal. Another kind of state-of-the-art one is one that we were working at in our group at Samsung AI, which basically takes this kind of Bayesian graphical model very seriously and does kind of modern variational inference for a Bayesian neural network of this graphical model, and actually comes out quite fast, and for the first time scales mammal up to VIT backbones, because most of the previous mammal papers have been using these kind of mini ResNet 10 backbones, which are super tiny. But with Meta NIW, you can scale it all the way up to model modern backbone. So that's pretty cool. Okay, so that's a bit of intro to gradient-based meta learners. I'll take a mini interlude to talk a bit about theory. So you might think that all of this stuff is a bit like, how do you know if this is going to work? Can you give any guarantees? And so there are some papers that, well, many papers that try to look at meta learning from a theory perspective. And I'll try to give a very light introduction to this kind of analysis that people do. But for the context of the meta learning theory, I'll show one kind of typical standard deep learning theory bound. So what people normally derive is some kind of equation that says like your test error, your guaranteed test error on the left is going to be less than your empirical train error, which might go to 0 if you have a deep learner, plus some measure of your deep neural network complexity. And so this measure over here has a number of data points in the denominator and something about weight norms in the numerator. And unfortunately, many of the bounds come out with something like that is exponential in the number of layers. So because this term here is exponential in the number of layers, as soon as you have a big neural network, this term is definitely much greater than 1. And then even if your empirical train error is 0, then the whole bound is meaningless because you are just saying the empirical test error is, yeah, so meaningless bound. So the question is whether we can have a low training error and also keep this term as low as possible, right? So this is the kind of thing that theory people worry about. And now if we go to the corresponding bound for meta learning, you end up with something like the guaranteed test error on a novel task is less than the empirical train error over all of your meta training tasks, plus 2 complexity terms, one of which relates to task-wise overfitting. So like how much you can overfit on your support set and fail to generalize to your test set. And the other of which relates to meta overfitting, which is like how much you can memorize all of your training episodes and then fail to generalize to a new testing episode. And for this kind of bound, the numerator complexity terms now, one of the things that they come up, the important thing is that they turn out to be, the whole equation is very big, but they turn out to be monotonically increasing in the quantity rho, which is the distance you are allowed to move in weight space between the initial condition and the fine-tuning for a particular task, and which comes back to this kind of constrained meta-learning algorithm I was talking about earlier. So basically, if you can manage to make the whole meta-learning algorithm have a small radius here, so each task can be solved within a small distance in weight space from its initial condition, then this term could start to be small enough. And then you can start to see how you could potentially have guaranteed performance even for a few shot learning task, right? If you can both have low empirical error and small distances moved in weight space. So anyway, that's like a little interlude to tell you a bit about how is the theory for this space. Okay, so we covered gradient-based meta learning, which was the first kind of big category of meta learners. And then there's amortized meta learners, which I'll talk about next. So this is the ones which kind of fit more naturally into this framework of like inputting a training set into some algorithm parameterized by the meta parameter and outputting the model which you can use to help classify the test images, right? So the most famous of these is, of course, ProtoNet. Probably everyone knows about it. ProtoNet is motivated by the idea of a nearest centroid classifier, which is something from like Statistics 101 from the 80s or so. So in nearest centroid, you say, let's take all of our training data and make a kind of average of each of the training categories. And then let's classify the testing data by which of the training category averages it's closest to, right? So it's kind of like nearest neighbor, but faster because you don't store the whole training set, you only store the class centroids. And so we said meta learning, AKA learning to learn. So what aspect of the nearest centroid classifier defines how to learn? So that aspect is, of course, the distance metric. So here I showed a kind of Euclidean distance metric between the test point and the centroid, but it could be any other kind of distance metric, which you might parameterize by omega. And so all of the, many of the amortized meta learners are trying to basically learn this distance metric here. So in ProtoNet, they basically say, let's make a deep prototype per class instead of a shallow one, and then classify with Euclidean distance. but because of the deep embedding of the data points in the prototypes, then overall it's a nonlinear distance, right? And then we do this same kind of meta learning before find out like what's the performance on the val set given the protonet embedding of the train set, etc. So yeah, that's the classic protonet. How shall we measure distances between the test points and the prototypes? Skip that one, but just to say, so then coming to the kind of trends that have been happening in the amortized meta learning space since protonet, people went back to trying to really find a kind of neural richer distance metric here, rather than just the protonet that took the Euclidean distance between the test point and the support sets, right? But can we find a better distance metric to put here? So in relation that we did several years ago, we tried to learn a neural distance to put there. In things like deep EMD, they use Earth mover's distance to compare between the test point and the support set. And one of my favorite ones, Subspace Net, uses point to plane distance. So when you take your support set, rather than representing the support set in terms of its average, you represent the support set by fitting a plane through it. And then to classify a test point, you calculate the distance between the test point and the plane, rather than the distance between the test point and the centroid. And this is cool because it has better kind of extrapolation properties, because you get to use the fact that this is a plane. So if this test point is over here somewhere, you get the point to plane distance, right? So yeah, different kind of metrics to measure distances are one of the big trends. Another one of the big trends is to look at dynamic features. So this is kind of motivated a lot by metadata set that I mentioned earlier, which has a bunch of other sub data sets. And when you have all of these sub data sets, having one single feature extractor for everybody becomes quite suboptimal. So then many papers said, how can we have a feature extractor that dynamically adapts? So for example, a feature extractor that uses a hypernetwork, so some images determine the weights of the feature extractor, which you process the other images with. And that was very successfully done by Synapse in Europe a few years ago. And another kind of dynamic feature extractor people have looked at for metadata set is to like train a classifier on each of the known data sets, and then basically think about how to fuse those different representations. Because you have a classifier on each known data set, then for a test point, you can have like 10 different embeddings of the test point from each of the neural networks of the known data sets. And then they reason about how to fuse those embeddings from all of the 10 feature extractors that you have. And so then the meta learner here is like the transformer operate of this URT model is the transformer that says how to fuse them. So that's dynamic features that help deal with like very different data sets in all of your tasks. Another kind of major trend has been what I'm calling, for lack of a better word, joint inference. So in Protonet, you get the representation of each category independently of each other by averaging the support images, right? But what you might really like to do is to kind of look at all of the support categories jointly and say, okay, let me represent them in a different way so that they are kind of maximally distinct from each other or something. And so this is the kind of thing that like Pete did in CVPR a few years ago. Basically, they take the embedding of each of the support categories and put it through a transformer that reasons jointly about them before doing the kind of distance metric from the query image to these support prototypes. And another actually quite large family of meta learners, which is for some reason not popular in CVPR community, but very popular in Europe's ICML community, are these neural processes, which are basically doing almost the same as this, but kind of wrapped up in some fancy formalism of neural processes. One thing interesting is that there was an evaluation paper last CVPR that looked at few-shot regression as opposed to classification, and then evaluated all the meta learners to say who's the best at few-shot regression. And they found that these neural process family of methods were actually the best at few-shot regression. So maybe this is something we should not overlook as much, even though they haven't been so popular in CVPR community historically. And then to mention a kind of cool state-of-the-art amortized few-shot learner, there's this one that I alluded to earlier, which is this so-called visual prompting paper. So in this example, they basically want to do like one-shot semantic segmentation. So your support set here is this horse image and the annotated mask of the horse. And then your query set, your test image is here, and you want to see if you can fill in the mask of this test image, right? And so they trained this one-shot semantic segmentation model by having many episodes, which are 3 images like this as input, and then this image is output where you need to indent the square, right? So this is exactly one of these amortized meta learning problems where this F here is your amortized learner. They don't call it amortized meta learning, but that's exactly what they are doing. And then with this framework, you can do like one-shot edge detection, one-shot colorization, one-shot segmentation, etc. So that's a kind of very recent state-of-the-art amortized meta learner. Okay, so that's now we covered the kind of big categories, gradient-based and amortized meta learners. One thing that is kind of a very apparent debate if you follow the few-shot learning benchmarks closely is whether transfer learning approaches or meta learning approaches are really better in terms of winning the few-shot learning benchmark leaderboards. So you'll see conflicting opinions about this. So for example, there were a whole bunch of papers that said, we don't need to do all this meta learning stuff. For example, if we just do very good pre-training and very good fine-tuning, there were a whole bunch of papers in recent years that said you can beat the leaderboards this way. So simplify your life from all this meta learning stuff. So some papers said this, some other papers said the opposite. They said, things like unicorn I mentioned said that properly tuned mammal works great, etc. So you might say, which group of people do we believe? Any opinion, by the way, who's on the, I guess you guys are in my meta learning talk, so hopefully you are not like totally against meta learning. But anyway, so we did some work to try and get to the bottom of this problem. And one of the ways in which we try to disentangle this issue is by looking to develop meta learners which are agnostic to the choice of feature extractor. So in mammal, of course, the whole point about mammal is learning the initial condition of the feature extractor. So we don't want to do mammal, but if we can find a meta learner that's agnostic to the choice of feature extractor and still helps, then at least we can say that meta learning is definitely complementary to transfer learning. We can't say necessarily come to the bottom of which is better, but we can say that it's complementary at least, right? And so I'll briefly mention 2 bits of work we did that tried to get to the bottom of this question. The first was meta-QDA in ICCV a few years ago. So the assumption of meta-QDA is that you have a fixed pre-trained feature extractor, which can come from self-supervision or whatever, download your favorite foundation model off of Hugging Face. And then what we want to do is to learn the classifier layer so that the composition of the new classifier layer and feature extractor performs well. So typical linear readout transfer learning, but how can we improve that learning of the classifier layer? And so the key idea is to try and learn a Bayesian prior on classifier layers so that we can do a better job of learning that linear readout layer for a new few-shot problem. So in Bayesian world, we say like we've got our support set for the new target problem. We want to learn the posterior distribution over the new classifier layer, and we do Bayesian learning together with some prior over the classifier layer. And then once we've got that distribution over classifier layers, we do our inference of query given support for test episodes integrating out over the unknown classifier layer. Okay, if you are not a Bayesian person, when I was a beginner Bayesian, I always thought these things looked like magic, and I had no idea what people were talking about when they said this. But one reason why you might want to have a distribution over classifier layers and integrate it out is that any one particular choice of classifier layer might be overfitted to the support set and fail to generalize to the query set, right? But the nice thing about all of the Bayesian things, if you actually model a distribution over them, then you avoid that preemptive overfitting to a support set. And then when we do our episodic learning, we are basically searching for the prior over classifier layers, which gives good query performance given support. So how do we concretely instantiate this? You could have a normal linear classifier layer for which there are tractable priors, but it turns out that it's actually interesting to have a QDA. Anyone remembers QDA? Anyone like old enough to have done statistics 101 before everything became deep learning? No. So QDA is like, you basically, it's kind of like ProtoNet. So you have a kind of mean for every category, but you also have a learnable covariance for every category. And where in ProtoNet, this covariance is like identity. And so now the question is, can we learn this mean and this covariance is what you would be learning for that classifier layer. And then now we need a prior for that. And if you go all the way into your old Bayesian textbooks, you can find there is this very nice prior called inverse Wishart prior, which has conjugacy properties with this Gaussian. And then it collapses all of these abstract looking integrals into like concrete things which you can execute in one line of PyTorch. Yeah, so now you do the episodic learning, you have closed form solutions for your classifier posterior, closed form solutions for query given support, and you can learn the optimal prior during meta training. And this works out pretty well. You get, for example, like 4% improvement over meta opnet, which was a really good kind of classifier layer meta learner before. And so the summary here is that all of this is with the fixed feature extractor, right? And so we can get 4% improvement over the next best thing that people did without even touching the feature extractor. So all of this is purely using meta learning to learn a prior for your decoder. So the claim we want to make is that meta learning is kind of complementary. So much more recently, we also observed that, especially on this meta dataset benchmark, all the people who are winning the benchmark leaderboard, like this paper's here, are basically having a very good initial model and then doing some kind of selective fine-tuning. We freeze some layer and fine-tune some other layer, or we insert some kind of LoRa adapter module somewhere and we update that module and freeze the other layers, etc. But basically all of this raises the question of which layers do you freeze, which layers do you fine-tune, where do you put your LoRa adapter modules into your foundation model, etc. And so but where is exactly like one kind of meta parameter of how to fine-tune. If you're going to do fine-tuning, you have to say, which thing do I fine-tune, which thing do I freeze, right? And so we basically did exactly this kind of typical meta learning pipeline over many fine-tuning episodes, but now set the meta parameter to be a mask of which ones to fine-tune and which ones to freeze. So basically in the whole compute graph, we always have like, are we going to fine-tune one layer, freeze one layer, etc. And then the meta learner finds that out for us. And because this which to fine-tune or not is a bit very discrete, we searched it with evolutionary search. Yeah, that's just a technical detail. And basically you can find some really nice masks like this. It's not a very obvious thing of like fine-tuning the first layer and freezing the fine-tuning the first half of the layers and freezing the first half of the layers and fine-tuning first half, freezing second half is a typical thing that people might do, but actually the fine-tuning masks you get something like this, which are a bit hard to interpret. But if you follow those fine-tuning masks, you get like solid improvement on the previous state of the art from last CVPR. And this kind of where to fine-tune or not, you can scale all the way up to VITs and get super high performance. So basically to summarize, is meta learning useful for few-shot recognition? We can't quite say if it's better than pre-training fine-tuning in a head-to-head comparison, but it's definitely complementary because you can both meta learn the prior of your output layer, which the foundation models don't tell you, and you can also use meta learning to answer the question of what's the best fine-tuning strategy for a given off-the-shelf foundation model. So it's surely complementary to your favorite foundation model, even if we don't know yet whether it's better than just large-scale pre-training of foundation models. Okay, so hopefully I convinced you of that. So the next topical thing people might be interested in is how meta learning relates to in-context learning, which I was also alluding to earlier. So of course, the kind of canonical famous in-context learning is this kind of language model stuff where you have got some sentences and labels as context, and then you have support set in our terminology. Then you've got a query sentence and you want to predict the query label as positive like this. And these things are of course trained on vast numbers of prior sentence completions, right? And the funny thing about all of this is that even though the sentence completions that you train it on are random internet sentences, you have this kind of nice emergent in context learning property, even for kind of classification problems like this. But this kind of sentence completion thing is actually very similar to our amortized meta learning objective we saw before, right? Basically, we input the first half of the sentence here into like the train set, and then we process it through our algorithm parameterized by omega, which is like the forward pass of your GPT or whatever. And then you check the validation performance, which is like the token you need to complete. And then you sum that over the performance for many different sentences, right? So you can see it's like almost the same as what we were doing in meta learning anyway, but for a kind of slightly noisy set of data of this training and validation set, because random internet sentences, right? But then there was a nice paper in last ACL, which said, if you then take one of these emergent in-context learning models and we explicitly do meta learning for it, so we take data that is more of this kind rather than random internet sentences, and we actually do exactly this, then you kind of substantially improve the performance of the emergent meta learners. So the take-home message is, anyway, they're doing something kind of like meta learning anyway, but if you make it more like meta learning, the performance improves. So that's one thing to say. Coming back to vision, though, people looked at ways to leverage the emergent in-context learning ability of language models for vision. So there was this nice Frozen paper a couple of years ago that said, let's take a pre-trained language model that has in-context learning already from emergent in-context learning, and then basically freeze it and train only a visual encoder with the captioning objective. And so training this visual encoder with a captioning objective kind of aligns the vision and language model. And then you can do things like this. This person is happy, this person is sad. What does this person look like? Sad, or whatever. So you kind of leverage the fact that you can use the language in context learning, having aligned the vision and language models. And then following that kind of step, like this year at iClear, there was this meta learning vision and language bridges paper, which does something more similar, but with explicit meta learning rather than this kind of emergent in context learning. So basically they have the image encoder, the language encoder, language decoder, and then this kind of single mod, and the image and language encoders are both frozen, and they are learning this single module that maps from the image encoder output to the language decoder input. And then, which is pretty similar to what the Frozen paper was doing, except now they do it explicitly with meta learning, and they basically do MAML of this. So this mapping module, they learn the initial condition for, and then in any one episode, they fine tune that initial condition on the support set. And it turns out that if you do this also more explicitly like meta learning, then you substantially improve over the previous results of Frozen, which relied on the kind of emergent version of in-context learning rather than the explicit meta-trained version of in-context learning. So yeah, hopefully that kind of is helpful to contextualize a bit the connection between meta learning and in-context. So then, yeah, coming towards the end now, I can talk a little bit about applications. So one observation I have is that as a community, we are super keen to make very strong conclusions from the results of one benchmark. So mini ImageNet was super popular in CVPR few-shot learning community, and everyone says, oh, some kind of meta learner works, some kind of meta learner doesn't work. This is like massively preemptive, trying to read too much into a very small amount of data, right? So I think we should have a much wider suite of benchmarks. If you ask some statistician, what information do you need to make a claim about whether model A is better than model B? They'll tell you that your sample size for that statistical test is the number of data sets. So until we have like number of data sets greater than 30, then we shouldn't be making any claims about which model is better than which other model, right? So anyway, aside, one thing we did, for example, is to make this meta audio benchmark. So we take a bunch of audio things, translate them into pictures with spectrograms, and then run all of the usual image meta learners on it. Like, can we recognize how a duck sounds from how a swan sounds, whatever, in all of the normal like vision few-shot learning stuff. And the results are totally different. So unlike the mini ImageNet ones, where the amortized learners are often leading, now the good gradient-based few-shot learners like meta curvature are massively ahead. And also the supervised pre-training is far behind. If you just do supervised learning on the meta-trained tasks and then try to do fine-tuning on the meta-test tasks, the performance is much worse. So this is like quite different than the kind of main body of results on mini ImageNet, and shows that we should really like try to resist overfitting our conclusions. As another different benchmark, this one will take a little bit of explaining. So in the context of communications, one thing you might want to do is to send some data over a noisy channel. So you have your Wi-Fi, you have your 5G, whatever, you're watching a video over 5G. And what normally happens in the conventional system is that the broadcaster does like JPEG, H.264, whatever it might be, then LDPC, then QAM to actuate the radio. Then on the other side, you do QAM decoding, blah, 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 JPEG decoding, etc. You get back the image, and hopefully you can watch your video without any interference, without any distortion, even if there was interference on the radio, right? And that's because these kind of LDPC and QAM layers are trying to broadcast it over the radio in a way that is both compact yet redundant. Redundant is an important part because then when there's noise in the radio, in the actual signal, you go into a tunnel or something, it doesn't completely break your video streaming, right? So then that's the very classic thing to do, still how it's mostly implemented in practice. But now there's many papers that say if you replace all of these classic things with a big neural network that map directly from pixels to the amount of current that you put on your radio transmitter, then, and you train this neural network, you can do much better than the classic pipeline. And basically this, you can think about this neural network training as kind of like training an autoencoder, right? So you have some input, you put it to an encoder, you add some noise to the encoding, which represents the noise on this radio channel, then you decode it, this neural network, and then you check the difference between the decoded image and the original image, and you optimize the neural network parameters to minimize that difference, right? Hopefully it's intuitive. And people found you can get like many orders of magnitude improvement by training this nice neural network rather than the classic thing to do. But this depends on whether you can learn the neural network that optimizes for encoding with respect to a particular kind of interference. So if you have trained this encoding neural network on like microwave interference, but then when you deploy this whole system, you take your phone into a tunnel, and the tunnel gives you some kind of multipath interference because the signal is like bouncing around inside of the tunnel, then you have distribution shift between hair and hair, right? And so then all of these nice, like super cool neural codes then go back to being worse than the classic codes. So the key thing you want to do here, finally getting to the point of this digression, is few-shot adaptation to distribution shift. So what you'd like to do is you take your phone into the tunnel, the noise properties start to change, and then you do few-shot adaptation of this autoencoder and maintain the super high like neural codec performance. And so exactly for this kind of problem, we had this benchmark in previous NeurIPS benchmark track, which is all about providing this kind of radio data and letting you benchmark how well your meta learner does. And some nice things about this compared to the popular vision benchmarks is that you can control the task complexity, like you can control, it's because there's a lot of syntactic data, you can control how different the meta-trained tasks are to the meta-test tasks, you can control how diverse the meta-trained tasks are between each other, etc. All of these things which are a bit like in vision, people always ask you like, how do you know if your source tasks are similar enough to your target tasks? This is something which we don't have a very clean way to quantify in vision, but for these kind of signal processing problems, we actually can. And again, the results are very different in this benchmark. So for example, meta curvature is also winning this benchmark, even though it's far from winning mini ImageNet. So again, the big point is, yeah, people are super over fast to draw strong conclusions from too few benchmarks, in my opinion. Also, you can have pretty pictures from this kind of benchmark. So you can, rather than having tables of numbers, you can show people, okay, this is some crappy other meta learner, and this is my nice meta learner. It's like encoding encoding the picture in a much more high fidelity way when broadcast across the noisy channel, right? So yeah, if that's interesting, you can check that out. And then finally, another thing which I think is kind of a forefront challenge in meta learning is task similarity. So basically, in many ImageNet, all the tasks are basically so similar. You can take a pre-trained foundation model and do linear readouts, and the foundation model covers everything. The tasks are so similar, there's not much to adapt. Like those kind of simple methods do pretty well. So we wanted to come up with a benchmark that encompassed like one-shot segmentation, one-shot key point regression, one-shot classification, one-shot pose estimation, etc. And we are going to draw tasks from all of these task families. And the question is whether we can transfer knowledge across all of these task families. And so because these are more different task families, feature adaptation might become more important. Yeah, we really want to push kind of general purpose meta learning rather than over engineering solutions to each of the subtasks. So this is something we are really excited about. Also, the benchmark is set up to let you directly compare kind of multitask and single task meta learners. So you can run separately like a one-shot segmentation meta learner and one-shot key point regression meta learner and one-shot classification meta learner, or you can try to have a single meta learner that knows how to generalize over all of those things, and you can try and compare the two. Also, it's really nice because we carefully designed this to be light enough for universities. So if you were previously struggling with doing meta learning on Google meta dataset and you said, oh my gosh, those Google guys have so many GPUs, it's taking me like 14 hours to run one hyperparameter of meta dataset. This Meta Omnium, despite having more tasks, is actually really light, 3 gigabytes in size. And even if you have woefully out-of-date hardware like a GTX 1080 Ti, you can do the whole run in 2 or 3 hours. And also there is a super clean hyperparameter optimization protocol. So as you might or might not know, a lot of the time for the popular computer vision benchmarks, it comes to people end up doing like overtuning their hyperparameters to win the benchmark, and then it's not clear what's the real scientific answer to things, or who just spent the most like tuning the parameters on the test set effort. So we were very careful to have an HPO protocol that both lets you tune like single task hyperparameters or cross task hyperparameters, etc. So yeah, this is something you can check out Tuesday PM. We have a poster about Meta Omnium. And yeah, so it's just some final remarks. I think in terms of the outlook and the challenges, multimodal task distributions are important. So things where the tasks are more similar than more different than episodes drawn from many ImageNet. So kind of schematically here, if you have some task distribution, there might be multiple modes in that task distribution rather than like one single mode. And also meta-train, meta-test distribution shift. Okay, this is something that comes up in like cross-domain, few-shot learning, etc. We still don't have a very good solutions to this. In terms of gradient-based meta learners, as I said before, I think more like novel choices of meta parameters are something which is very promising, not just tweaking around the initial conditions like MAML, but really coming up with more innovative ways to model and represent how to learn. Better benchmarks are terrible. Meta dataset and Meta Omnium are like small steps in a better direction, but we really need better and more data sets so we can have kind of statistically significant answers about which meta learner is better. Something very important. And of course, meta learning beyond the classification. So most of our popular benchmarks at the moment are classification ones, Meta Omnium, etc., and the meta channel coding and stuff before I showed something in that direction. But luckily, we have a whole session later on this morning about meta learning beyond the classification. So you'll be able to hear more about that. And yeah, that's it for me. Any quick questions Or we can turn over to Yanwei, I guess.
Have a break.
Okay. Oh yeah, yeah. I forget. Was there a break on the schedule? Probably.
Yeah.
Yeah. Okay. How long is the break?
We should start in the
15 minutes.
Yeah, yeah.
Okay. 15 minutes break. See you in a bit.
I call it this conference of opinion, but I'm also interested in the time series.
Okay.
So if I started the application of visual learning, meeting that is well integrated, like.
So one sec, I think they want to start, maybe we can, you can introduce, I mean, anyway, the audio is waiting for Yanwei to, the audio, one sec, let's just make sure the next one is working.
Hello. It's working?
Yeah.
Okay. Hi, let's back to our tutorial. Let's start.
Sure. We can hear the.
Okay. Hello. Can you hear me?
Yes.
Okay. Let's start my part. Okay. Thanks for Team's nice talk and good morning, everyone. Thank you for joining us today. We're excited to share our part, the future learning by statistics method. So my name is Yanwei Fu from School of Data Science, Fudan University. So due to the visa problem, I can't do the in-person presentation, and I got COVID several weeks ago, so I still have cough a lot. So I will introduce the first part of this talk, and my senior PhD, Yi Kai Wang, in the room, who working on this topic, will cover the remaining parts. Let's revisit feature learning from different angle. Okay, data collection, pre-processing, and labeling are expensive human tasks. So in terms of this cost, fully supervised learning uses the entire data set to train the model with corresponding label for each input. This is the most straightforward type of learning method, as it assumes the label for each image are given. However, labeling is a tedious process, and often input data come in unlabeled. So semi-supervised learning aims to address this problem. How do we use a small set of labeled data and another set of unlabeled data to optimize a model for a task that we are trying to solve? So semi-supervised learning can be described as an intermediate form of unsupervised learning and supervised learning. So future learning here aim to teach the machine learning model how to learn from only a small number of labeled training data. So the goal of future learning is to enable model to generalize a new unseen data sample based on a small number of samples we're given. Therefore, future learning could dramatically reduce the turnaround time of building machine learning application, emerge as a low-cost solution. So if we only have unlabeled data, we can do unsupervised learning and self-supervised learning. So unsupervised learning, including many methods for learning from unlabeled sample. Self-supervised learning is one specific type of method to learn from unlabeled sample. Typically, self-supervised learning identifies some secondary tasks, while labels can be automatically obtained and train the network to do well on the secondary task. On the other hand, in terms of the quality of label, learn with noisy label refer to situation while the label in the training data are not always accurate or correct. So this happens when the label are collected from the website. The presence of label noise in training data can greatly reduce the accuracy of model. And this talk will cover some algorithm on semi-supervised learning, future learning, self-supervised learning, as well as learning with noise label. So let's imagine what thing happens from future learning to managed learning. So we illustrate the key-shot data on binary classification task with continuity, cluster, and manifold assumption, which are the general assumption in semi-supervised learning. So from few to many labeled example, hypotheses learned from large amount of example are favored than those trained with few example. Moreover, good hypotheses should prefer geometrically simpler decision boundary and encourage points in the same cluster to have the same label. This should be a general principle for task agnostic pattern of a hypothesis. And the feature learning use the N-way K-short classification approach to discriminate between N classes and K example. We summarize the setting here, and this is quite common knowledge to feature learning. So unlabeled data, on the other hand, carry rich task-related information. They are proven useful for future learning of language model. The question is how to effectively make use of such unlabeled data. One way to do this is by revising the self-training technique for language model. Fine-tuning present state-of-art prompt-based future learner. So for unlabeled data, it generates a pseudo labels as weakly augmented data. And this simple approach is shown to outperform the other supervised or semi-supervised benchmark task. So it works for NLP. How about our vision task? Can we using the feature learning with unlabeled data as a semi-supervised learning task? In NLP, feature learning can be applied to various tasks like task classification, sentiment analysis, language translation. As it works quite well. And in our computer vision, feature learning can be applied to like image classification and the feature object detection and reconstruction. So in robotics, feature learning can enable robotics to quickly learn new tasks based on a few examples. In NLP, in-context learning is a prompting tactic that allows the model to process example before attempting a task. So it can be considered as an emergent property of large language model and was popularized after GPT-3. So in context learning is kind of similar to feature learning as I mentioned in Tim's talk, in that it allows the model to learn from only a small number of examples. And that more application will be covered by Yuxiong's talk. Let's give some visualization of feature learning leaderboard on benchmark dataset, meta dataset. So during the past years, we can see the curve from very beginning, which is very low to very high. And this means that algorithm can rapidly acquire new skills, knowledge, and with good performance. So what is required for feature learning? As we want to achieve learning capacity trained with many examples using a few trained data, it is necessary to break a standard supervised learning pipeline. In the first majority capacity required by feature learning is the prior knowledge. We want to have some prior knowledge instead of from training scratch, typically. So such prior knowledge can be learned from a large and relevant dataset, such as ImageNet, and we can also acquire another major capacity is the fast adaptation capacity. Although we have learned some common knowledge from the large base dataset, we still have to adapt it to the novel task with only a few examples. So the straightforward pre-training fine-tuning pipeline using the large base dataset to train a feature extractor and only train the classify when adapting to novel classes to reduce the learning difficulty. And the team gave very good survey and about meta learning. So meta learning aims to learn the fast adaptation capacity from few examples on base dataset, such that it is more intelligent on learning from few examples than standard learning framework. So what can statistics do for future learning? The first point is how to understand future learning in statistics. In general, future learning can be formulated as a posterior estimation problem in statistics. We regard the knowledge learned from the base data set as a pride for the data distribution and updates the posterior when observe the new task. Although better mirror the similarity of instance of distribution can greatly help future learning method. Then, what can be used in statistics to solve future learning? The most common meta-learning follows the Bayesian inference in statistics, which is already introduced in Tim's talk. On the other hand, many methods using Gaussian process to help the construction of future learning model. And also exist several interesting concepts in statistics that are beneficial for future learning, which we will introduce next, including causality, calibration, outlier detection, statistical outlier detection, alignment, and yeah. Okay, maybe you want to share next.
Okay, thanks for Professor for the introduction. Now we discuss future learning by statistical methods in details. Firstly, we will introduce a range of statistical concepts that prove beneficial for leveraging base data in future learning. Subsequently, our attention will shift towards novel data, where we will discuss strategies for enhancing adaptation. Finally, we will conclude by envisioning the future of future learning in the 2020s and exploring potential avenues for further advancement. In the first topic, we will talk about three concepts: causality, similarity measurement, and neural collapse. Let's start with causality. Causality deals with understanding the causal and effect relationship between variables or events. It provides a deeper level of understanding compared to correlation, allowing us to reason about how changing one variable influences another. Incorporating causal reasoning into future learning can offer significant advantages in terms of generalization and adaptation. First, we can use causality as part of probability program induction for future learning, such as Bayesian networks, structural equation models, or causal graphic models. Causal reasoning can also facilitate transfer learning by understanding the causal relation between different tasks. The learning algorithm can transfer knowledge from one task to another one more effectively, and remove the knowledge that cannot generalize to new tasks, which is known as the pre-knowledge. In particular, we can guide the learning process towards discovering the causal factors that are relevant for the task at hand and remove the spurious features. The Cognitive Science 2015 paper by Joshua Tenbob presents a framework called Bayesian program learning that can learn a large class of visual concepts from just a single example and generalize to in the way that are most indistinguishable from human. The framework brings together three key ideas: conversationality, causality, and learning to learn, which can be utilized for classification, parsing an object into parts, and generalization on new examples, as well as generalizing on new concepts from related concepts. On a challenging one-shot classification task, the model achieved human-level performance while performing recent deep learning architectures. The first challenge we encounter in future learning is determining what we can learn from the base data set. When simple fine-tuning focuses solely on what to transfer from the base data set, the meta-learning pipeline takes the question of how to transfer by explicitly learning the capacity of fast adaptation on the base data set. Yet NIRPS 2020 addressed the influence of pre-trained knowledge in details. A common assumption is in future learning that a stronger pre-trained model leads to better performance. However, an interesting paradox arises. As illustrated in this figure, a stronger model does improve average performance when the query sample is not similar to the plot samples, the performance actually dropped. To understand why this happens, consider the following example. The support set contains images of lines in gray grass. and dogs in yellow grass. This non-causal relation misleads the future learning model and causes misclassification. In this case, a stronger pre-trained model is more severely affected by this prior knowledge, and therefore, pre-trained knowledge may not always be beneficial in future learning. To solve this problem, they construct a structural causal model to formulate the dependency of future learning. The prior knowledge D influences the feature representation X, and both of them will influence C, which is the transformed representation of X, usually in a low-dimensional manifold. And the classification effect Y, like the probability logits, is determined by X and C. An ideal future learning model should capture the true causality between X and Y instead of simply correlation to generalize to unseen samples. To push the true causality between X and Y, we need to use the causal inversion to model the probability of Y giving to X instead of the likelihood of the probability of Y giving X for the future learning objective. To implement this, we need to find the stratification of the pre-trained knowledge DI, which can be captured via feature-wise from the last layer of pre-trained models or class-wise from the pre-trained classifiers. Then we can obtain the backdoor adjustment to stratify the confounder to obtain a more robust future learning model. We can also consider the causal relation directly from the image space. For example, as current future learning models are trained with the image level annotations, both the causal, that the dog, and the non-causal feature, the people, the tree, and the grass, are trained to build up correlation with the class annotation dog, which can lose prediction ability and be less effective on novel data. To see this, we can construct another sample generation graph as in the figure, where we have the class Y, the causal feature S, and the non-causal feature Z. The class Y influences the causal feature S, and the class Y and non-causal feature Z will generate the sampling procedure C, where C equals 1 indicates the sample X is in the training set, and C equals 0 indicates the testing set. As a non-causal feature exists, the data sampling is biased and different in training and the testing stage. To reduce the data selection bias, we propose an augmentation method called batch mix. We exchange the visual and the label information between query images and some random images. Through the mixture, we can break the dependency between causal and non-causal features. Specifically, consider the new causal graph. Now the data generation process have different passes. First, we only have the causal features, and second, part of both causal features and non-causal features are replaced by other images. And the third, all the causal features are replaced. For the first case, the patch is only containing causal information, and we can naturally decrease the influence of non-causal features as it removes the mixtures from other patches that may be spurious. Well, for the second case, the generated patching integrates S and Z randomly from two different images and breaking the original sampling procedure that S and Z come from the same image. In this regard, the causal feature S no longer depend on Z. Thus, we can make it possible to eliminate the non-causal features if the model is trained well. Well, for the last case, the causal features are completely removed. The patterns of original non-causal features are broken and are randomly replaced by others, making the correlation between the non-causal features and Y no longer exist. So in all these cases, we can solve spurious correlations problem by exchanging visual and label information between images. Another concept is learning a better matrix. Previous matrix learning method employ a deep neural network to extract some features and replace the final FG layer with a distance function, for example, cosine distance and Euclidean distance. Some may introduce more deep distance distance function and extra network modules to refine the similarity comparison. Such distance function directly compute the distance between training images and testing images and get the probability that for classification, which bypasses the difficult optimization problem in learning a classifier for future learning. Then it is straightforward to ask, can we learn the better metric by introducing some probability distribution? In the following, we will introduce several works on this direction. The first work is DPMD, which is introduced in Tim's talk. DPMD utilizes the Earth mover distance in future learning. It models the similarity based on transportation cost between query image and the spot image. The EMD generates the optimal matching flow between structural elements that have the minimum matching cost, which is used to calculate the image distance for classification. Another work is the Brownian distance correlation between query and spousal images, which to measure the discrepancy between the joint distribution of their embedded features and product of the marginals. The BDC is implemented via regarding each channel of the features as an observation. Then we can construct the Euclidean distance matrix within an image and between different channels of the features. After normalizing distance matrix, we can directly compare different images via a correlation of the distance matrix within different channels. SEN is a substitute to the Euclidean distance in ProtoNet with an interpolation of both Euclidean distance and the norm distance to force the embedded points to be extracted to extract prototypes and being repealed from all other prototypes, keeping the norm of all points in the same. And the last concept we will cover in this topic is neural collapse. Neural collapse is an important phenomenon in the training procedure of neural networks. Basically, the features, intravariance variation, and the classifier will collapse during training. As visualized in the figure, the green squares represent the vertices of the standard simplex ETF. Red balls and sticks represent the linear classifier, and blue ball and sticks represent the class means, and these small blue spheres represent the last layer features. For all objects, we distinguish different classes via the shade of the color. As a training process, we can observe 4 types of neural collapse, including the first, the last layer features collapse on their class means, and the second, class mean coverage to the vertices of the simplex ETF. And the third, the linear classifiers approaching their corresponding class means. And finally, all the classifiers act like the nearest class center decision rule. This is the neural collapse in standard supervised learning, and Guarantee has provided theoretical and empirical results about neural collapse in the context of transfer learning, especially in future learning. They demonstrate the neural collapse generalizes to new data points and new classes, and in the presence of neural collapse, training a linear classifier in top of a learned deep model can be done using only few samples. To verify this, we could adopt some metric of class distance normalized variance, which is used to capture the variance of features. And when this metric approaching 0, neural collapse comes. As shown in this figure, when increasing the number of source classes as in the lines of different colors, the presence of neural collapse in the target classes strengthens, as we can see more classes will approach the more like 0, this metric. And the corresponding field shot performance is also consistently improved when the overall number of source classes is increased. Hence, neural collapse generalizes to new source samples. It emerges for new classes, and its presence immediately facilitates the good performance in future learning. Then we can think, what can we do to use neural collapse in future learning? Liu takes advantage of stronger regularization by boosting the probability of the first two neural correlates properties when training on imbalanced data. And Yang, on the other hand, make use the second neural correlates to adopt a fixed ETF classifier and train other parameters in the model. This model can be used in few-shot incremental learning, and we can plug learnable layers between fixed backbones and fixed classifiers, and we can directly pre-assign the classifiers prototypes to the simplex ETF to reduce the learning difficulty and ensure the feature class alignment in an incremental fashion. Now we turn our attention to the adaptation of novel data discussed strategies for enhancing adaptation from a statistical perspective. Specifically, we first discussed how to achieve semi-supervised few-shot learning in a safe way when we have access to unlabeled novel data. Then we discussed how to calibrate the prediction of few-shot learning model from a prototype and distribution perspectives. When regarding few-shot learning with unlabeled data, as a semi-supervised learning, one of the straightforward pipeline is to use the self-taught learning pipeline. First, we could use the labeled data to train a few-shot model, and then we can inference the stool labels of the unlabeled data and expand the training set with some readable subset of the stool labeled images. It is noteworthy that although the learning performance is expected to be improved by those unlabeled images, some empirical studies show that there are situations where the use of unlabeled images degenerates the performance. Thus, it is advisable to be able to exploit unlabeled data safely. And our core problem is how to ensure that the selection of stool labels is credible to benefit the learning. Safe semi-supervised learning aims to ensure the credibility of each component in the semi-supervised learning pipeline. Li Yifeng has done several very good works in this topic and motivates us to consider safe semi-supervised learning in few-shot learning. Generally, for a learning algorithm, we should consider credibility from view of data quality, model uncertainty, and measure diversity. The unlabeled data is uncontrolled and may mislead the learning model, so we should be careful on how to model the data distribution. And for the learning model, we need to explore which separator is the best for the discriminating models and decide which data distribution is better for the generating models. And for the evaluation of learning model, the credibility requires a safe prediction with diverse measures. So to implement safe semi-supervised learning in few-shot learning and to ensure that the selection of stool label is credible, we design a linear system with noisy data indicator between network features and one-hot labels. We can add a noisy data indicator gamma to represent the noisy data explicitly. For clean data, the linear relation between network features and one-hot labels is strong. Thus, we should have a small or even zero gamma. And if the data is noisy, a large gamma will return by the linear system to better fit the noisy feature label pair. Basically, the gamma can be regarded as a residual prediction error, which is a baseline method to identify noisy data in the training set. However, this raw residual fail to detect outliers in the leverage points. A better way is to use some statistical testing to test whether the predicted residual is large based on other observations. And this is equivalent to test whether gamma equals 0 in this equation. But this only works when we only have one noisy data. And when there are multiple outliers, we have several problems like masking and swamping. Masking means that the multiple outliers may mask each other so that they will have a very small t if we only sample one example and test it based on the other observation. And swamping indicates that when the multi-outlier will increase may lead to a large T for clean data. So we must consider the training data in the same formulation to solve the whole indicator matrix for all training data at the same time, leading to this equation. Now our target is to solve gamma and identify noisy data based on gamma. This noisy data will have non-zero solutions, and our optimization objective becomes MSE loss and some penalty on gamma. As we only care about the solution of gamma, but we still have some unknown parameter beta, but we find that the beta have fixed the solution if we fix the gamma. So we can do some calculation transform from the objective into a standard linear regression with some sparse penalty on gamma. Now the only problem is how to choose the sparse coefficient lambda. A number of methods for determining lambda exists. For example, some heuristic rules, some use cross validation, and use data adaptive technique, also some information criterion, but none is suitable when the label is noisy. And we don't have a proper method to choose lambda in advance. This inspires us to sequentially consider all available solutions for all sparse variables along the solution path by regarding the solution of gamma as a function of lambda. Then when lambda turns to infinity, the solution of gamma will turn to 0. And with a proper penalty, for example, the row-wise L2 vector norm, the gamma will vanish row by row, that is instance by instance. Then we can use the lambda where gamma turns into 0 to rank the data and denote the last vanished instances as noisy data. Recall that in our motivation, clean data will lead to 0 gamma and the noisy data will lead to a large gamma. Then in the solution path, clean data will vanish at first and noisy data will vanish at a large lambda. This solution path can be calculated by the GMNet algorithm. And we have a GF to show the solution path. Different lines indicate different instances, and the red one is the most clean data estimated by our algorithm. As well, statistical algorithm, we have a very sound theoretical guarantees to ensure the effectiveness of our algorithm, which we only give an informal version here to extract the main results with a less restrictive condition. Our algorithm will identify the subset of ground truth null data with no false positive errors, and with a more restricted condition, our algorithm will identify all the noisy data. For more details, please see our CVPR 2022 tutorial for details. And this is an example of using sparsity to help future learning. We next consider another active concept, calibration. We recall several core problems in future learning. One is the learner representation are biased towards the base tasks, that several novel classes are grouped together. And the other is the learner representation is easy to overfit on future examples. And in general, calibration aims to avoid the above biases and make the robust estimation. The bias towards base classes come from several potential reasons. For example, some common knowledge exists in different novel classes, like a background, or some similar patterns exist in different novel classes, where the variants are not embedded by the deep network. We have discussed this problem from the causal perspective. Now we introduce calibration to separate such grouped class. This calibration can be implemented via the information from nearest neighbors. Specifically, we could model the samples with pairwise distance and re-rank the distance by consider the learning as a retrieval task, giving future examples as anchor points. For example, in the left figure, we have 4 nearest neighbors of sample 1. And for each neighbor, we could also find its 4 nearest neighbors, which is possibly a neighbor of sample 1. Then we can use such extended nearest neighbors to calibrate the pairwise distance to maintain the manifold in the novel task. Another way to calibrate is for some tasks, different classes may require for a different threshold instead of a simple 0.5. Hence, we can also calibrate the probability of normal classes via a Gaussian mixture model. And we can also calibrate the distribution of novel data with the help of base data. This can be achieved with a Gaussian distribution assumption of each class. Then we can adopt samples from the base classes that are similar to the novel classes to help estimate the Gaussian parameters. Or we can use a more complex optimal transport model to benefit such calibration. And sometimes we may want to use a nonlinear classifier to do feature learning compared with linear classifier, which is not so easy to overfit on feature examples. Nonlinear classifiers are very easy to overfit on feature training data. Then we can use Bayesian approach to reduce the overfitting problem via prior nonlinear model that can be learned from base classes. This is also a meta-learning approach. And finally, let's look forward to see what is future learning could be in 2020s. We will focus on 3 different types, that is updated backbones and some cross-domain future learning algorithms. And finally, the foundation model as future learning learners. The traditional future learning adopt a base data set to learn some feature extractor and use novel data to learn a classifier or do field step fine-tuning. And it's in nature to ask, can we enhance the future learning with recent development of deep learning? The first attempt is a thorough investigation of the training backbone and training pipeline. Current CumNet backbone already see the benefit of deep architectures, and who at CVPR 2022 push its development into stronger architectures such as Vision Transformer, with a simple protonet plus VIT backbone pre-trained with CLIP, which is a yellow star in this figure. The future learning performance is increased by a large margin. Such an improvement requires a combination of a larger pre-trained dataset. As a comparison, the VIT trained from scratch only achieved about a half accuracy, as shown in the blue square. They also suggest that the off-the-shelf pre-trained models are not optimal for out-of-distribution future learning tasks. Thus, the meta-learning to learn the fast adapting capacity and task-specific fine-tuning also benefits the future learning task. The other attempt is an efficient transformer tuning method to for future learning. We can formulate the attentive prototypes by aggregating patch embeddings with the corresponding attention weights of the class tokens for each image. And we can provide the model with the button task-specific information and guide each self-attention layer to aggregate more class-related features. As we only have few examples, we must fix most of the network parameters that are frozen and only update a few parameters. We can additionally adopt the lightweight domain residual adapter in the form of learnable offsets to deal with the potential failure of our ABT on large domain gaps. With this algorithm, we may avoid meta training and still enjoy the benefit of large-scale pre-trained models. Another question that has recently gets more and more attention is cross-domain future learning. Typically, cross-domain future learning enables the discrimination between source data and the target data such that we cannot obtain common knowledge from source data. Here are examples of 2 benchmark datasets, cross-domain future learning datasets. The learning model needs to transfer knowledge learned from ImageNet and to domains like out-of-domain categories, for example, CT images, and the fine-grained domains, for example, different kinds of leaves. Given such a challenging task, 2 core questions exist. The first is how to improve future learning with only a source data as a training dataset. The second is, could we utilize some target data for further promoting the cross-domain future learning? We explore several methods to answer this question for the data augmentation and source target alignment. For the single source cross-domain future learning, first notice that obvious visual shifts can be observed between the source and target data. This motivates us to tackle cross-domain feature learning by augmenting the visual styles of source images. To augment diverse new styles for source images, we propose a novel style tag method. Visualization results show that we can generate both virtual and hard styles, where the hard means that our model will first attack the region that is used to recognize the class labels. And for learning cross-domain feature learning with field labeled target data, we have a source training data, a target training data, and target testing set. We think that obtaining field labeled examples for each category is more realistic than collecting unlabeled examples in the most cases. In this case, we still take the general feature learning setting and ensure that the classes of the target training set and the target testing set is strictly disjoint. Though with more data, there are still challenges to be solved, and several works to solve these challenges. For example, generalized MET-FT mix-up, MET2N, and TGDM. Due to the time limitation, I will not dive into details of this method. Now let's look at the foundation models. Foundation model has revolutionized the way we approach machine learning. Foundation models are a class of neural networks that have been trained on vast amounts of diverse and high quality data. They have demonstrated an extraordinary ability to learn from relative few examples and generalize their knowledge to new unseen tasks. This has made them incredibly versatile and powerful in solving complex problems across different modalities. To name a few, we have some text-to-text images, which is GPT, and the text-to-image models, which is a generation model, and image-to-text models, which is we can use for vision question answering, and some image-to-image tasks, which we can use some reference image to prompt the learning task as in context learning, such that we can do several image translation tasks in a unified large model. For example, this in painting, outpainting, and novel view synthesis. These foundation models have emerged as a remarkable future learners capable of tackling diverse tasks and across multiple modalities as they continue to explore their capabilities and push the boundary of what they can learn. We are witnessing a new area of machine learning, and that holds tremendous promise for a wide range of applications. In here, we just introduce a few of foundation models as future learners, which is Flamingo. Flamingo is a family of vision language models that can rapidly adapt to various images and video tasks with a few annotated examples. It was developed by researchers from DeepMind, Oxford University VGG Group, and others. Flamingo model can handle sequences of arbitrary interleaved visual and textual data. For example, the image, text, and image, and the new text. Then we can bridge powerful pre-trained vision-only and text-only models and fix them, and only to learn some module to align these models to achieve state-of-the-art results on various multimodal tasks. By simply prompting the model with task-specific examples, we can Flamingo outperforms the model fine-tuned on thousands of times more task-specific data. And finally, the in-context learning. Where foundation models demonstrate the remarkable zero-shot capabilities is still far short on more complex tasks when using the zero-shot setting, and few-shot prompting is a way to use as a technique to enable in-context learning, where we can provide the demonstrations in the prompt to steer the model to better performance. In NLP tasks, a natural few-shot prompting is providing several training examples, and along with the desired output for an input sentence to, at the end of the input, and ask the model to complex the sentence to the unfit example to naturally do the few short task. And in computer vision, we can also do few short prompting via the vision in context learning, which can let the model learn to generate the images guided by the reference image given as in context pairs. Now the take-home message is to learn feature learning by statistical methods. We could, for learning from base data, we can learn causal features that are truly transferable to novel tasks. We can model the similarity measurement in a more statistical way, and we can utilize neural collapse to benefit feature learning. And for adaptation on novel data, we can ensure the safety of learning with unlabeled data via statistical outlier detection, and we can calibrate prototypes to reduce the bias and calibrate the class distributions to prior knowledge. And for the future learning in 2020s, we can benefit future learning with deeper architecture and more powerful pipeline, and tackling more challenging cross-domain future learning, and finally adopt the foundation model that future learners. And these are the members of our future learning group. Dr. Yan Weifu is the team leader and our supervisor, and Dr. Chengming Xu, Dr. Yuqian Fu, and I are PhD students and the guidance of Dr. Fu. And I'm Yikai Wang, and I work on statistical sparsity for learning problem, and I'm currently seeking a short-term visiting and the potential postdoc position in the upcoming years. It would be much appreciated if there is any available opportunities. Please send me an email or talk to me if you are interested. And that's all. Thanks for listening to the talk. And Professor Yan Weifu is online if you have any questions. Any problems?
Yes.
So if no problems, we may go into the next session. Professor, may unmute the Michael.
Can everyone see my slides and hear from me?
Yes, we can see your slides.
Okay, cool. Okay, great. Hello, everyone. Thank you for attending our tutorial. I'm Yuxiong Wang from UIUC. So far, we have covered important mental learning and statistical approaches to address few-shot learning, mainly in the context of image classification tasks. In this session, we will discuss how to extend these techniques to deal with in-the-wild few-shot learning tasks that go beyond simple classification and recognition. Meanwhile, we will explore together and delve into a critical question. What additional tools and methodologies are required to effectively address the complexity of real-world few-shot learning scenarios? More specifically, our focus has primarily centered around the conventional few-shot image classification, which typically involves only RGB images and assume a reasonable base and novel class split given in advance. However, real-world scenarios introduce a significant level of complexity that extends across multiple dimensions. Regarding task complexity, diverse modalities, and compound factors. First, the tasks become increasingly complex. Starting from classification, we would like to address how to localize, detect, and segment novel objects and recognize their actions and interactions from limited data. In addition to these discriminative recognition tasks, we also consider how to synthesize objects in novel viewpoints and poses from few or a single image, reconstruct their 3D shapes, and even predict their dynamics from few historical data. Beyond visual concept learning, we would like to enable agents to learn novel skills from sparse demonstrations. More broadly, few-shot learning is not limited to computer vision, but it exists in a variety of fields and disciplines. Second, the real world consists of a diverse range of modalities, such as cameras, radar, LiDAR, X-ray, ultrasound, language, and their interaction. Humans are inherently learning in a multimodal fashion. Therefore, few-shot learning needs to be investigated in a multimodal context. Third, in practical applications, the challenge of limited data is often compounded with other environmental factors, and they collectively have a more significant impact. For example, long-tailed distribution. Real-world data are distributed in a long-tailed manner, where a few classes have large amounts of data, while many classes are rare in the tail of the distribution with limited data. Also, domain shift. Data in the real world may not resemble the data on which the model is developed. Therefore, combined few-shot learning and domain adaptation allow models to adapt to new domains using limited examples from the new domain. And more broadly, open word and open vocabulary recognition. Categories of data are not fixed, and new categories can emerge over time. Hence, the combination of a few-shot learning and open vocabulary recognition provides a more accurate and comprehensive modeling of the ever-changing world. Let's first consider few-shot recognition. Discuss how we extend the few-shot learning and mental learning techniques from simple classification to deal with more challenging recognition tasks with structured outputs, as well as other compound factors and modalities. It is relatively straightforward to extend conventional large sample object detection to the few-shot scenario, following the setting in few-shot classification we discussed previously. The objective now is to learn an object detector for novel classes when only a few examples with annotated bounding boxes are available. But the task becomes more challenging. Unlike image classification, detection requires not only classifying, but also localizing potential multiple objects within an image, as well as dealing with distracting background regions. The way to tackle few-shot detection is similar to few-shot classification by transferring knowledge or meta-knowledge from base classes with large amounts of annotated bounding box examples. Similar to few-shot classification, a common framework is based on meta-learning, like gradient-based MAML or metric learning. A two-stage training pipeline with episodic learning is commonly adopted, which consists of mental training and mental fine-tuning. Under this framework, different kinds of strategies are introduced, including feature reweighting like FSRW and mental RCN, or model weight generation like mental DT. On the other hand, Few-shot detection can be also accomplished using a simpler transfer learning framework, commonly called two-stage fine-tuning approach, TFA. In the base training stage, the entire object detector is trained on base classes. In the few-shot fine-tuning stage, the feature extractor is frozen, and only the box predictor is fine-tuned on both base and the novel classes. This framework offers several benefits. First, simplicity. Employing transfer learning removes the need for simultaneous training and inference, or embedding an additional mental learning, which increases the complexity of the standard detection pipeline. Second, flexibility and extensibility. Following work shows that this two-stage fine-tuning can be improved, for example, by modifying the training process like the second stage, or introducing additional plug-and-play components. Specifically, the conventional fast RCN architecture includes an RPN, an RCN head, which is followed by a box regressor and a box classifier. In decoupled faster RCN, DFRCN, shown on the left, stop gradient is performed between the RPN and the backbone. Meanwhile, scale gradient is performed between the RCN and backbone, as well as the decoupling conflict tasks between the classifier and the regressor. On the right, a hallucinator network is introduced that learns to generate additional useful training examples for novel classes by transferring the shared within variation from base classes. Such a decoupling or data hallucination is shown to be helpful in fine-tuning on novel classes, leading to significantly improved detection performance. Few-shot semantic segmentation can be formulated in a similar manner as a few-shot detection, and similar transfer learning and mental learning approaches have been developed. While most of the work mainly emphasizes the performance of novel classes, recognizing all classes is also crucial, as test samples may contain any instance in practical applications, which requires a few-shot models to learn new concepts without forgetting. To this end, generalized few-shot learning approaches have been introduced for classification, detection, and segmentation, which recognize novel classes while maintaining good performance on base classes. Beyond the focus on solely on object as in detection segmentation tasks, recent work starts to investigate compositional learning of human-object interactions, HOIs, in low data regimes. This extends few-shot concept learning from nouns only to combination of verbs and nouns, therefore enabling a context-dependent reasoning of the relationship between humans and objects. A benchmark is constructed accordingly, where positive and negative images only discriminate on action labels as illustrated in this riding bicycle example. 4 distinct test sets with a varied combination of seen and unseen are proposed for evaluating different levels of generalization. The red form denote an object or action class that is available in the training set, and the blue fonts indicate those held out unseen ones in the test set. So we can say that existing few-shot learning methods have been shown to struggle on this task, in particular regarding generalization beyond seen concept during training, despite their strong performance on few-shot classification benchmarks. This suggests that significantly more efforts and advances in few-shot learning mechanism and methodologies are needed for real-world application, such as visual relationship reasoning. Okay, as we have just discussed, the standard few-shot learning setting assumes base and novel class split to be null and requires supervised example for novel classes to be given. However, the visual world we live in is intrinsically open, streaming, and dynamic, with new categories on concepts emerging over time. Therefore, a very important and relevant problem is object discovery, aiming to separate objects from background in an unsupervised manner. What makes this task especially challenging is that the notion of an object is inherently ambiguous and context dependent. For example, in the right figure, it is unclear what should be treated as objects and what as background. Slot attention is recently emerging and widely used paradigm for object discovery. It performs a single step of image encoding with a scene, followed by a spatial attention operation, which is used to bind a set of compositional variables called slots to image locations. The slots are then decoded individually to reconstruct the image. This simple model is able to successfully segment the object in toyish data set like Cater, but completely fails in realistic regimes with a complex background, such as the street driving scene shown on the right. This is because in this situation, the appearance alone is not sufficient to separate the objects from the background. The key insight then is, while the ambiguity of the object definition is not resolvable in the static image world without direct supervision, it has a natural resolution in the dynamic world of videos. Here, dynamic objects are considered, which are defined as entities that can move independently in the world. This video also provides a strong bottom groping signal. Independent motion which localizes the moving object from the background. Notice that the moving object points to the object that move in the current frame. But the dynamic objects include both moving and non-moving objects as long as they can move. Objects that cannot move, such as the trees, are not under consideration. Now we will discuss how to introduce such motion cues into the slot attention framework and scale it from toyish images to realistic videos, demonstrating how motion segmentation can be used to improve object discovery. A spatial temporal memory module is first introduced, which enables extending the architecture to videos of arbitrary length. Then the slot attention is applied to generate the compositional features. For the first frame, a learnable initial state of the slot is used, which enables passing both densely and sparsely populated scenes. Then each individual slot is broadcasted, and the attention masks are used to construct the single feature map. This design saves memories and scales well to realistic scenes with a large resolution and dozens of objects. Finally, an independent motion prior is incorporated, which provides an actual learning signal to guide the slot to focus on the dynamic objects. These key modifications, especially the motion cues, enable the whole model to successfully learn separating dynamic objects. Motion segmentation is conducted with the optical flow as input. Compared with the moving object ground truth, right? The motion prediction is sparse and inaccurate. But even this weak learning signal is sufficient to guide the model to separate dynamic object from the background and generalize to a static instance of these objects. Concretely, to guide the attention masks, the sparse motion segments are first padded to match the number of the slots, and the matching is found between these two sets. Notice that here supervision is only given to the matched pairs, enforcing the model to learn only from positives. Visualization show that the model can clearly capture most of the visible object and also generalize to static objects. Though major achievements have been made, one main limitation is that the RGB reconstruction space is too complex to discover objects, especially in real-world regimes. The key insight then is, instead of directly reconstructing in the RGB space, a better strategy is to reconstruct in the middle space of quantized features called tokens. This leads to an advanced framework with motion-guided tokens. The bottom video illustrates the learned slots and tokens. We can see that the motion-guided tokens provide a mid-level structured reconstruction space, which can represent boundaries and surfaces of the input images, therefore benefiting object-centric learning. So the slot representation can then capture most of the dynamic objects, including pedestrian vehicles, no matter if the object is moving or static. It can further find a new object when it moves to the next frame. More specifically, for release videos, both foreground and background are more complex, making the reconstruction in RGB space very challenging, even with the motion guidance. Intuitively, optimizing the slot features in a more structured space, like a quantized feature space, could be able to overcome this limitation. To this end, a VQ-VA is introduced to quantize the feature space, and then these discretized features are denoted as tokens. Now the pipeline is modified in the following way. First, the motion-guided slot learning is directly conducted on videos. The slots will form an instant-level representation to find individual objects. Next, instead of directly reconstructing the RGB space, the slots are bounded to the mid-level token space learned from VQ-VA. The slot and tokens are trained jointly, so that the motion cue and the token representation can be linked together. We now investigate existing approaches to object discovery from a meta-level perspective. There are two typical solutions. The first one aims to find an easier reconstruction space, such as optical flow space and depth space, in addition to the VQ token space. The other one focuses on learning a more powerful decoder. We ablate these key design choices regarding the reconstruction space and the types of decoder in a unified framework to comprehensively evaluate their contributions. So the ablation study shows that the capacity of decoders plays a key role in object discovery. A more powerful decoder will bring significant improvement. Meanwhile, the VQ space yields the best performance as a reconstruction space. Also, given sufficiently strong decoder, reconstructing in depth or flow space doesn't bring further improvement compared with RGB, but can even decrease performance. So the combined VQ space and the perceiver decoder achieve the best performance so far. The object discovery we discussed relies on motion cues from videos. What if we don't have any motion cues? Or even more challengingly, what if objects come from a new target domain without any explicit labels? Let's look into the task of unsupervised domain adaptation for object detection. The images show an example of adapting an object detector from a labeled source domain to a new unlabeled target domain. In the source domain, where the weather condition is normal, the detector can learn to identify vehicles and pedestrians from object-level labels. However, when this detector is applied to the real world, the weather condition may change, and the decoder needs to discover vehicles and pedestrians without any human supervision. This task brings new challenges because there is zero data label in the shifted target domain, but we still aim to achieve fine-grained object-level recognition. Contrast mean teacher addresses this task of unsupervised object detection in a shifted domain, with the key motivation coming from identifying the intrinsic synergy between two unsupervised learning paradigms. On the left side shows mean teacher self-training, which is developed for unsupervised domain adaptation. On the right side is a momentum contrast for unsupervised representation learning. They actually share several interesting similarities. First, for both paradigms, they learn two encoders, one in an online fashion, while the other is the momentum of the online version. Second, both encoders take inputs from two different views of the same unlabeled images. Third, the momentum encoder's representations serve as keys for training the online encoder using detection loss or contrast loss. Inspired by this alignment, contrast mean teacher uses the teacher detector's predictions to discover objects in the unsupervised target domain and treat them as pseudo labels to supervise the student detector. In addition to the unsupervised branch of the mean teacher, labeled source domain data are also utilized to build a supervised branch that ensure the student performed well in the original source domain. Here's the central design is this object level contrastive learning between the teacher and the student, in which object level features from the teacher and student are extracted and refined. Objects of the same predict class should be similar in both models both models of feature space, while objects of the different predicted classes should have dissimilar features. This object level contrastive learning enhances feature learning or unlabeled objects in the target domain, thus leading to effective unsupervised domain adaptation for object detection. So far, we have mainly focused on learning with a single RGB modality. And the classic few-shot learning benchmarks usually make use of few-shot samples from a single modality. By contrast, the real world consists of a diverse range of modalities. And importantly, humans are naturally multimodal learners and use cross-model information to learn new concepts accurately and efficiently. This capitalizes on multimodal few-shot learning. So let's first focus on multiple visual modalities. A very representative application is autonomous driving perception, where the constraints of time and budget, coupled with the diversity of visual modalities like cameras, radar, and LiDAR, inherently limit the variety of the domains that collect training data can adequately represent. Therefore, efficient knowledge transfer is desired, where knowledge learned during training is transferred to the test time model in a new domain. One line of work studies cross-model adaptation, where training and deployment of the model happens in different data domains. Another line of work explores cross-modality adaptation, where training and deployment leverage different set of modalities. More recent work, DoCross, considers simultaneous domain gap and modality gap between the training and testing phases, representing a more challenging and realistic setting. More concrete, DoCross considers camera and LiDAR modalities being available during training, and only camera is available during testing. Under this scenario, surprisingly, using the additional modality as a direct supervision, that is taking LiDAR as depth supervision, in fact leads to worse result than not using it at all. To account for this challenge, DoCross introduced a knowledge distillation strategy to transfer the LiDAR knowledge into in the training phase to the camera model in the testing phase. So more specifically, DoCross includes three components. First, the LiDAR teacher uses a voxelized LiDAR point clouds to transform the image features to the bird's eye view BEV frame. It provides essential knowledge on how to guide image learning given LiDAR information. Second, camera student is supervised by the teacher model as well as the LiDAR ground truth. In addition, two discriminators are used to align features from source and target domains. Here shows a day-to-night adaptation scenario where DoCross is compared with direct LiDAR supervision and an adversary learning model. DoCross leads to more stable and consistent segmentation results. So with the recent advance in vision, language learning, and the large pre-trained foundation models, an important direction is to leverage the language modality to facilitate few-shot learning, which, for example, helps reduce ambiguity as illustrated by the improved classifier decision boundary shown in the left figure. So as a representative example shown in the right figure, the Flamingo model, right, which we talked about earlier, this visual language model shows strong in-context few-shot learning capability for various image and text understanding tasks with few-shot prompting. For example, on the top, the question is generic about single object. The second row requires external knowledge, and the last row requires reading text. Consequently, there is growing interest in adapting large pre-trained models for few-shot learning. As a brief summary, some work fine-tunes a vision or language encoder to achieve few-shot learning. Another line of work trains a mental learner to efficiently bridge large-scale vision and language model and leverage their already learned capacity. Finally, another work aims to achieve few-shot learning without any training. More specifically, the first line of work uses prompts tuning to maximize the model performance. The key is to find the optimal context tokens to maximize probability of predicting ground truth labels. During this process, the image and text encoders are both frozen. The learned prompts significantly improve the performance of a clip in image classification. As shown here, the clip models predict more accurate labels with the help of better prompt tokens. In addition to prompt tuning, instruction tuning concerns better aligning the vision models with the language models, as LM seems to generalize better to the user's intentions. The architecture is quite simple. The vision encoder is a pre-trained clip encoder. After processing the images, the visual tokens ZV are projected to the dimension of language tokens. Finally, an LM is used, which is a llama here, to jointly process the visual and language instruction tokens and generate the language response. The key to aligning vision and language model lies in generating instruction following data. That's why it is called instruction tuning. As in the figure, right? So the ground truth, bounding boxes and captions of images are converted into numerous conventional texts. Such a text serves as the training data of the model presented in the previous slide. Okay, so there are also additional approaches where modules are designed and glued to align the representation from images and large language models. In the example of BLEEP 2, QFormer is used to align visual tokens as input to the LLMs. Compared with tuning-based method, another work proposes to phrase both vision and language encoders and train mental learner to bridge the two modalities. Specifically, this mental mapper generalizes shared mental knowledge by sequentially observing tasks in a learned visual prefix, which is then used to guide the language model into generating relevant interpretation. As shown in the figure, this method achieves great VQA performance. Experiment also show the improvement of using self-attention over MLP-based learners. So another work, tip adapter, is a non-parametric training-free adapter, which obtains the weights not by SGD training, but from a cache model constructed by the few-shot training set. In this way, the feature extraction by adapter could also be viewed as retrieving the few-shot knowledge from the key value cache. Surprisingly, TF adapter with such training-free initialization achieves on par or even better results than clip adapter with training. In addition, TF adapter could be further enhanced by fine-tuning for just a few epochs, achieving good trade-off between efficiency and performance. Okay. So far, we have discussed exciting progress in various discriminator recognition tasks in few-shot regimes. Now let's shift our focus to more challenging generative synthesized tasks. Compared with few-shot recognition, few-shot synthesized remains relatively underexplored, but has gained considerable attention in recent years due to the rapid advance in generative modeling. We will start from 2D synthesize, then move to 3D synthesize, and the future synthesize or prediction, and finally discuss the interaction between synthesize and recognition. Similar to few-shot recognition, the few-shot synthesized task can be formulated in the following way. We are given a large amount of data in the source domain and the few-shot reference images in the target domain. In extreme few-shot cases, the number of images in the target domain could be only around 10, for example. The goal is to obtain a generative model in the target domain. The key challenges here are twofold. we need to preserve both the quality and the diversity of the generated examples, whereas the model is adapted from the source domain to the target domain. In principle, this formulation can be applied to different types of generated models. However, each model may encounter its unique challenges. 2D few-shot synthesized models can be roughly grouped into 3 categories. Fusion-based method fuse different features from few-shot examples. Transformation-based method discover category irrelevant attributes and then added them on the few-shot examples to generate more examples. Fine-tuning-based method, which are also the most prevalent these days, design certain strategies to fine-tune the generated model from source to the target domain. As a representative work on fusion-based method, Lofgren in the training state samples a set of key-shot training samples from the source domain and encourages a model to learn transferable generation ability to generate new images from the given few-shot images. Then in the test stage, the model takes a few-shot images in the target domain as input and generates additional samples. The limitation of a fusion-based method is that the generated samples heavily rely on the few-shot images fed into the model, therefore lacking the ability to generate diverse samples. Delta GAN belongs to the transformation-based method. As its name indicates, Delta GAN aims to learn the transformation delta from one sample to another. It contains a generation subnetwork and a reconstruction subnetwork. The reconstruction subnetwork takes as input the base sample X1 and the transform sample X2 and outputs the transformation delta between the 2 samples and the reconstruct S2. The generation subnetwork replaces the input of X2 with the Gaussian noise and also outputs the transformed image and the corresponding transformation. The losses applied on the feature extractor DI enforce the reconstruction constraint and also enforce the generated sample X2 delta to be in the same category as the real transformed sample X2, which indicate that the transformation is category irrelevant. And the adversary loss is further used on the transformations generated by the 2 subnetworks, encouraging the generation networks to yield similar transformation as the reconstruction network. The key idea of a fine-tuning based method is to efficiently transfer the knowledge from the source domain to the target domain. Do contrast learning implements this idea by applying contrast learning on both the generator and the discriminator. For the generator, it aims to maximize the mutual information between generated images in the source and target domains originated from the same noise input. For the discriminator, it pushes away the generated target images and the real target images to prevent collapsing to the few-shot target set and enable the model to generate diverse samples. With these strategies, the fine-tuned generator can inherit the knowledge from the source domain to generate diverse samples on the target domain. While fine-tuning based methods typically focus on how to preserve the knowledge from the source domain as much as possible, recent work suggests that this needs to be done in a very careful manner, as highlighted in the framed images. When blindly preserving all the information from the source domain to the target domain, existing methods could suffer from severe quality degradation on the synthesized images due to transferring incompatible knowledge to the target domain. To address this issue, knowledge truncation is proposed, with the key idea of identifying the incompatible knowledge by estimating its importance during fine-tuning. So feature information is used to estimate the importance of weight matrices. The information contained in these matrices is then regarded as incompatible knowledge during adaptation. Therefore, those weight matrices that have a low importance are pruned, leading to a model that discards the incompatible knowledge on the target domain. Expanding upon 2D synthesis, 3D-aware image synthesis requires understanding of the underlying 3D structure and generating images that maintain multi-view consistency. This becomes particularly challenging in the few-shot regimes and need to leverage advanced in generative visual models and neural rendering. More concretely, in the few-shot novel view synthesized task, the model is required to generate the novel view synthesized result with only few reference views. This is typically accomplished through conditional neural ratings fields nerve, which basically learn prior knowledge like geometry priors from other instances and use it to construct a novel view according to the few-shot views. Recent work suggests a different perspective, which directly generates a nerve representation that matches the reference views at given camera locations, and then renders novel views from nerve. One example along this line is DiffRF, which incorporates diffusion-based generation into nerve. The key idea is to inject rendering into the diffusion process of a nerve by approximating the sample nerve during training. In this way, an approximation of the final sample nerve can be obtained using gradient, enabling optimization through rendering, similar to the standard nerve optimization, but without the requirement of time-consuming sampling. After training, this model is able to generate diverse nerve representations that align with the reference views. As shown here, DiffRF generates visually feasible results with high diversity. Compared with the 2D synthesized task, the scarcity of available data set is much more noticeable in 3D synthesized tasks. In 2D tasks, there is a wealth of a large-scale data set that can be used to supervise models. Often, large-scale general data sets are available to pre-train models that generalize to some extent to unseen domains. By contrast, most 3D tasks lack such a large-scale data set. It is common to perform per-scene training, which is not generalizable. And sometimes there are even no sufficient data to train the model. Given the inherent connection between 3D scenes and 2D images, a promising strategy to address 3D tasks is to leverage 2D knowledge or transfer knowledge from the 2D domain to the 3D domain. By doing so, 3D tasks can benefit from the abundant 2D data set and the powerful 2D pre-trained models, even in the absence of the 3D training data. Dream fusion represents such an idea and transfers 2D knowledge to address instruction-guided 3D scene generation. While prior work on 3D generation relies on conventional ancestral sampling for the diffusion process, Dream fusion introduces score distillation sampling SDS, which models the diffusion process as a gradient descent and distills from a pre-trained 2D generated model to guide the 3D diffusion. The intuition behind SDS is straightforward. It aims to generate a rendering result that resembles those produced by the 2D diffusion model when given the same instruction. This objective helps bring the two distributions closer together: the distribution of images generated by the 2D model and the distribution of the scene rendering result from random sample views. As shown here, Dream fusion generates 3D scenes with coarse texture. Not limited to novel view synthesis, we would also like to employ generative models for synthesizing or predicting the future dynamic states of objects and humans. We will discuss this task in the context of human motion prediction, where given a historical motion sequence, possible motion is predicted in the short-term or long-term future. In the few-shot motion prediction, the aim is to train a predictor model that can quickly adapt to a new task, such as adapting to the prediction of walking style motion using only a few training sequences by training the mental learner on eating and sitting motion, for example. The work of proactive and adaptive mental learning, PAML, shows how mental learning can be applied to few-shot human motion prediction. As a general meta-learning approach, PAML combines MAML with model regression network MRN. MAML is used to learn generic model initialization. However, the plain SGD updates used in MAML may not sufficiently modify model parameters for effective adaptation to novel tasks. Therefore, MRN is introduced to estimate a generic model parameter transformation for effective model adaptation in the few-shot setting. So far, we have talked about the few-shot recognition and the few-shot synthesis separately, but they are highly interconnected in various ways. One straightforward connection is to generate an RGB image based on a given semantic image, which is investigated in semantic image synthesis. In the few-shot semantic image synthesis setting, a model is trained in the source domain that can perform image synthesis on source labels. The model is then fine-tuned with few-shot samples on the target domain labels. This can be regarded as an inverse process of the discriminative model. A class affinity matrix is introduced to address the task by finding the correlation between source and target labels. A more in-depth bidirectional interaction between generative and discriminative learning is investigated in the task of joint few-shot recognition of novel view synthesis. Given only one or few images of a novel object from arbitrary views with only category annotation, we aim to simultaneously learn an object classifier and generate images of that type of object from new viewpoints. These two tasks inherently interconnected with each other. For example, the synthesized images can provide viewpoint variations for building a better recognition model. Meanwhile, the recognition model ensures preservation of the desired category information for view synthesis. A feedback-based framework, FBNet, is introduced to tackle this joint task, which consists of a view synthesis module and a recognition module, and they are linked together through feedback connection in a bow-tie fashion. The empirical evaluation shows that recognition and synthesis facilitate each other. The connection between generative and discriminative learning can be further extended to a multitask scenario, which is crucial for comprehensive scene analysis. So given a set of pixel-level prediction tasks like semantic segmentation, surface normal estimation, reshading, key point detection, edge detection, typically, we would like to learn a discriminative multitask model to make prediction for this task simultaneously. Here, we investigate how generative learning could benefit discriminative learning using two strategies, with one explicit and the other implicit. In the explicit strategy, a nerve-style model is introduced, which is able to render not only photorealistic RGB images, but also various accurate scene properties like segmentation, labels, surface normal, and edges. An alternative implicit strategy is to synthesize RGB images paired with only image-level scene labels by introducing auxiliary self-supervised or weakly supervised discriminative tasks. In both strategies, the paired synthesized data have been shown to be effective for data augmentation in low data regimes. Okay. For real-world agent, rapid visual concept learning is an important first step, but they also need to acquire novel skills from limited data. We will now focus on the key insight in the few-shot learning from demonstrations, which investigate how to utilize a small number of demonstrations to help solve reinforcement learning RL tasks. RL has been known for its sample inefficiency with sparse reward, especially when from scratch, as illustrated in the left figure. Suppose we train a robot arm to grab a cup or a banana. Our agents trained from scratch can only jitter around without getting any useful feedback. However, if we have demonstration leading to the items as shown on the right, though still far from perfect, the agent will know where to explore and have much higher probability to get reward feedback. And therefore, the agent will do much better. Well, we can also solve the task by imitation learning IL that mimics the expert demonstrations. The expert demonstrations are usually expensive and demand significantly human effort. This leads to an important question: how to do imitation learning and RL well with a few expert demonstrations. The key challenge here is that the few-shot learning from demonstration is brittle for two reasons. First, a few trajectories only cover a very small subset of state action space. The agent doesn't know what to do and how to recover, as long as it leaves the expert trajectory, as illustrated in this figure. Second, even if the agent stays on the trajectory, as steps accumulate, the agent has a quadratic growing chance to get away from the expert trajectory. Therefore, a good inductive bias is required, which essentially tells the agent what to do when they are not on the expert trajectory. Such inductive biases can be roughly grouped into three categories. The first inductive bias is closeness to the expert, with the idea that if the agent is now away from the expert trajectory, it should get back to the states where the expert trajectory is close. We can roughly further divide this idea into two types: distance-based and divergence-based. In the former, we try to find a distance function, usually over embedding learned by self-supervised learning to define closeness, and is more popular in the robotics community. In the latter, we try to use a classifier to determine which area is more often visited by expert instead of non-expert, and assign higher score to those areas. This is more popular in the offline RL and IL communities. Such a method can be either online or offline. One issue of the closeness to expert solution is that it doesn't use any specific property from non-expert data. However, demonstrations that are not expert to the target task can also be very useful. In fact, humans can summarize skills and accumulate experience from other tasks. Therefore, we would like to leverage prior knowledge of skills extracted from less related tasks in the past. Notice that as a subset of few-shot learning from demonstrations, skill prior is closely related to meta-RL and hierarchical RL. As illustrated in this figure. So the most popular skill prior solution in the past 2 years is the VAE architecture. It says skills as action sequences, which can then be encoded by a VAE encoder. The decoder takes the sequence embedding and decodes action step by step. Such a decoder can be viewed as a low-level actor in hierarchy RL, whereas a high-level actor is an MLP that mimics the outputs of the encoder by only seeing the current state. With the VAE train, the actor for the target task can be conveniently trained from few-shot expert data, and the corresponding skill is extracted by that actor. However, the VAE architecture requires many expert trajectories to work well to enable fewer shot or even one shot from demonstrations. Some other architectures have been proposed, such as the flow-based architecture, which encodes the priors in a set of one layer, normalizing flow from different tasks in the related data, and then trains a small MLP for coefficient that combines the output from flows for the target task. Such a method works well in one-shot settings, and because of the invertibility of the flows, it guarantees no dimension loss for the action space in later RL fine-tuning. So priors with generative models that extract skills have been prevailing in the last few years. However, the recent advance of language models paves the way for another promising approach and offers two important properties: the prompting mindset and the emerging generalizability. Prompts provide the ability to generalize without a single gradient update. Specifically, one way is to try to expert trajectory not as a target to fine-tune, but instead as a prompt, a hint for decision transformer, and then few-shot learning can be performed with zero actual gradient updates. An alternative way is to describe a few examples for the task as a prompt for large language models, which is feasible in some game applications. Then we can keep producing reward labels from large language model to train the RL agent. In addition, emergent generalizability allows the extension from NLP to RL task directly. For example, we can take a pre-trained large language model and fine-tune it to work on Mojoko RL environments as a decision transformer. So here, we provide a brief summary of the different inductive biases we have discussed. While we have mainly focused on the few-shot task in computer vision, the lack of data issue remains a universal challenge in nearly every machine learning-driven application. It will be equally exciting to address few-shot learning and extend mental learning in a broader range of fields and disciplines, as exemplified by the recent advances in AI for science. In summary, in this tutorial session, we have talked about the recent progress towards in-the-wild few-shot learning, covering tasks of increasing complexity, diverse modalities, and other compound factors. As concluding remarks, I would like to discuss some open-ended questions that revolve around the implications of pushing the boundary of few-shot learning beyond conventional classification. First, regarding the problem formulation, the existing base and novel formulation in few-shot learning remain narrowly defined and may not readily apply to various tasks and practical scenarios. On the other hand, several problems that are not traditionally considered as few-shot learning could potentially fit under this umbrella from a broader perspective. Moreover, it can be challenging to establish a clear separation between base and novel classes, making it difficult to access and making it difficult to evaluate the model's generalization capability. In certain cases, like few-shot detection or when using large foundation models, the novel classes may already be implicitly known during the base training phase, even without explicit labels. When it comes to methodology employed in few-shot learning, it is worth questioning whether current techniques such as mental learning or foundation model tuning are adequate. Consider the presence of compound factors. It becomes necessary to explore additional tools that can effectively address these complexities. In the case of dealing with heterogeneous modalities, the utilization of multi-model learning becomes essential to tackle the challenges presented. However, it is important to investigate whether the advancement made in few-shot vision language learning truly represent our understanding and ability to learn from limited visual information, similar to what humans are capable of. Finally, it remains a fundamental challenge to develop a universally applicable few-shot methodology that can be effectively employed across different fields. Correspondingly, what is a unified underlying statistical principle for small sample learning? These are interesting questions worth further exploration. With that, thank you all for your attention. I'm happy to take any questions.
Any questions? If there is no more question, we may end our tutorial here. And thank you for listening.